There is a star in the constellation Cygnus that is tearing itself apart, not slowly, not gently, not in the way you might imagine a candle guttering in a draught, losing a little wax here, a little flame there. This star is hurling the equivalent of Earth's entire mass into space every few years. Vast curtains of glowing gas, superheated plasma, reaching temperatures of tens of thousands of degrees, stream outward from its surface at hundreds of kilometers per second. These curtains form an expanding shell of lost material that has been growing for over 4 centuries. A nebula of rejected starlight, a cloud of atoms that a star could not hold on to. And this star is not exploding. It has not reached the end of its life. It has not detonated in a supernova or collapsed into a black hole. It is simply too luminous, too massive, too powerful to hold itself together. Its own light is ripping it to pieces. The star's name is P Cygni. For most of human history, it was invisible to the naked eye. Thousands of years of stargazing passed without anyone noticing it. Then, in the late summer of 1600, it appeared. European astronomers recorded a new star in the northern sky, a third magnitude point of light, where no star of that brightness had ever been catalogued before. It blazed for several years, faded to invisibility, returned brighter than before, faded again, and eventually settled into a faint but persistent glow that has continued to this very night. At the time, no one understood what they were seeing. It was not a nova in the traditional sense. It was not a comet. It was not a planetary conjunction or a trick of the atmosphere. It was something the astronomy of the 17th century had absolutely no framework to explain. What those early observers had witnessed, without knowing it, was a luminous blue variable in the grip of a violent eruption, a star so massive that the radiation pouring from its core was literally blowing its outer layers off into the void. Not destroying the star, not ending it, simply peeling it, layer by layer, year by year. What makes P Cygni extraordinary is not merely its behavior. Plenty of stars behave strangely. The sky is full of variables and transients and objects that defy easy categorization. What makes P Cygni extraordinary is what that behavior taught us. This single star became the key to understanding one of the most important and least intuitive processes in all of astrophysics, the process known as stellar mass loss. The idea that stars do not simply burn their fuel and die quietly, but actively shed their own material throughout their lives, sometimes gently, sometimes catastrophically, was a revelation that fundamentally reshaped our understanding of stellar evolution. And it was P Cygni, more than any other single object in the sky, that provided the observational signature to prove it. By the end of tonight, you're going to understand why the most massive stars in the universe cannot keep themselves intact. You are going to understand how a single spectral pattern, discovered through the light of P Cygni, became one of the most important diagnostic tools in modern astrophysics. You are going to understand why the process of stellar mass loss governs the fate of galaxies, the enrichment of the cosmos with heavy elements, and ultimately the existence of planets, oceans, and life itself. You are going to understand why losing mass is not a symptom of stellar death, not a sign of weakness or decay, but rather a fundamental feature of stellar existence. And you are going to understand why a faint, barely visible star in the neck of the Swan may have more to say about the origin of your own body than almost anything else in the night sky. Before we get started, if you love exploring the depths of space as much as we do, take a second to like the video or subscribe. It's a simple action, but it helps this channel reach more curious minds like yours. The story of P Cygni is a story about the tension between gravity and light, between the force that holds a star together and the force that tears it apart. It is a story about how the universe recycles its own material across billions of years, how atoms forged in the hearts of dying giants are scattered across light years of empty space, seeding the next generation of stars and worlds with the elements that make complexity possible. And it is a story about how a single faint, flickering point of light in a 17th century sky quietly, almost shyly, redefined everything we thought we knew about how stars live, how they age, and how they die. The answer it gave us was not comforting. The answer was that stars are not the stable, enduring beacons we once imagined them to be. They are storms, violent, luminous, self-consuming storms that pour their substance into the darkness around them, enriching the cosmos at the cost of their own existence. And the brightest storms blow the hardest. The most luminous stars shed the most material. The most powerful furnaces burn through their own walls. There is a lesson in that, if you are willing to listen. A lesson written in the blue-shifted absorption lines and red-shifted emission peaks of a spectral profile that bears the name of a star nobody had ever seen before the year 1600. Now, let's begin. To understand what P Cygni is doing, why it matters, we first need to understand the forces at war inside every star, because every star, from the smallest red dwarf glowing dimly at the bottom of the main sequence to the most luminous hypergiant blazing with the fury of 1,000,000 suns at the top, exists in a state of profound tension, a tug-of-war between two opponents that have been locked in combat since the moment the star first ignited. It is a balance so precise, so finely tuned, that even a small shift in either direction can trigger consequences visible across the galaxy. This balance has a name. It is called hydrostatic equilibrium, and it is the reason stars can exist as coherent objects at all. On one side of this balance is gravity. Gravity pulls inward. It wants to collapse every particle of stellar material toward the center, crushing hydrogen, helium, and heavier elements into an ever denser core. If gravity were the only force at work, every star would collapse into a point in a matter of minutes. The Sun, for instance, has a mass of roughly 2 nonillion kilograms. That is a 2 followed by 30 zeros, a quantity so vast that writing it out in full would fill a line of text with nothing but digits. All of that mass, all of that material, roughly 330,000 times the mass of the Earth, is being pulled relentlessly inward by its own gravitational field. Without something to resist that pull, the Sun would compress itself into an object no larger than a medium-sized city in less than an hour. Gravity does not tire. It does not take breaks. It is always there, always pulling, always trying to compress the star into oblivion. On the other side of this balance is radiation pressure. Deep inside the core, at temperatures exceeding 15 million degrees Celsius, nuclear fusion converts hydrogen into helium, releasing energy in the form of photons. These photons push outward. They collide with atoms, transfer their momentum, and create an outward force that resists the inward pull of gravity. In a stable star, these two forces are in equilibrium. Gravity pulls in. Radiation pushes out. The star maintains its size, its temperature, its luminosity. It is a dynamic equilibrium, constantly adjusting, constantly rebalancing, but on the whole, remarkably stable. This is what allows the Sun to burn steadily for billions of years, without either collapsing into a dense ball or flying apart into a cloud of dispersing gas. It is, quite literally, what makes a star, but here is where the physics becomes treacherous. The strength of gravity depends on mass. More mass means stronger gravity. This is straightforward. The strength of radiation pressure also depends on mass, but through a different and much steeper relationship. As you increase a star's mass, its core temperature rises, its fusion rate increases, and its luminosity climbs, not linearly, not proportionally, but as a steep power law that quickly leaves intuition behind. A star twice as massive as the Sun is not twice as luminous. It is roughly 16 times more luminous. A star 5 times the Sun's mass is roughly 600 times more luminous. A star 10 times the Sun's mass is roughly 10,000 times brighter. And a star 50 times the Sun's mass, an object in the same class as P Cygni, can be more than 1,000,000 times more luminous than our own star. This means that for the most massive stars, radiation pressure does not merely balance gravity, it begins to overwhelm it. The photons pouring out of the core carry so much momentum, deliver so many tiny kicks to the atoms in the outer layers, that they start to push material off the star's surface entirely. Not in a dramatic explosion, not in a single cataclysmic event, but in a continuous, relentless wind that strips the star of its outer layers, atom by atom, layer by layer, year after year, century after century, like sand blown from the crest of a dune by a persistent gale that never dies down. This is stellar mass loss, and it is one of the most consequential processes in the universe. To appreciate the scale of what we are discussing, we need some comparisons. Our minds are not built to process astronomical numbers directly. We need bridges between the familiar and the cosmic. So let us start with what we know. Consider the Sun. Our star does lose mass. The solar wind, a stream of charged particles flowing outward from the Sun's corona, carries away roughly 1.5 million tons of material every second. 1.5 million tons. Every second. That sounds enormous. It sounds like the Sun should be visibly shrinking, like a snowball left on a hot sidewalk. But compared to the Sun's total mass, it is negligible. Over the entire remaining lifetime of the Sun, perhaps another 5 billion years, the solar wind will strip away only about 0.01% of its total mass. The Sun's mass loss is, in cosmic terms, trivial. It is like a human losing a few skin cells each day. Your mass does not change in any measurable way. You would never notice. Now consider a star like P Cygni. P Cygni has a mass estimated at roughly 30 to 40 times that of the Sun. Its luminosity is somewhere between 500,000 and 600,000 times the Sun's luminosity, 500,000 suns condensed into a single stellar furnace. And its mass loss rate is not 1.5 million tons per second. It is closer to one Earth mass every few years. To put that number in context, the Earth has a mass of roughly 6 trillion kilograms. P Cygni throws away that much material in less time than it takes a child to finish primary school. Over the course of its entire life, spanning several million years, P Cygni will lose a significant fraction of its total mass. Perhaps 10 solar masses. Perhaps 20, simply blown away by its own radiation. Not in a final deathbed explosion. During its life, while it is still burning, still shining, still a functioning star. Imagine the Sun as a basketball sitting on a table in the center of a gymnasium. At that scale, the Earth would be about the size of a small peppercorn, sitting roughly 26 meters away. Jupiter would be a marble the size of a large grape resting at a distance of about 140 meters. Now imagine that basketball slowly dissolving, shedding tiny particles of rubber and leather into the air around it. Over the course of a human lifetime, you would barely notice the change. A few specks of dust drifting in the light. That is the Sun's mass loss. Now imagine a beach ball 5 times the diameter of that basketball, glowing white-hot and visibly deflating. Chunks of material peeling off its surface in real time, forming an expanding cloud of shredded matter around it. You could watch it shrink. You could see it diminishing, losing itself, growing smaller against the darkness. That is P Cygni. Or consider it from a different angle entirely. If you could drive a car at highway speed, say 100 kilometers per hour, and head toward the nearest star beyond the Sun, which is Proxima Centauri, at a distance of 4.2 light-years, the trip would take you roughly 45 million years. If you could somehow drive at the speed of P Cygni's stellar wind, roughly 200 kilometers per second, the same trip would take about 6,300 years. That wind is not gentle. It is a torrent, and it carries a river of matter with it, flowing outward into the galaxy without pause. Here is yet another way to grasp the scale. If you could somehow weigh the material P Cygni ejects in a single century and pile it onto the surface of the Earth, that material would outweigh every mountain, every ocean, every continent on our planet combined. It would outweigh the Earth itself many times over. And yet, compared to P Cygni's total mass, that century of loss is modest. The star can sustain this rate of loss for hundreds of thousands of years before it is significantly diminished. It is losing itself, but slowly, catastrophically by human standards, gradually by cosmic ones. The wind itself is not something you could see with the naked eye, even if you were close enough to try. It is not a visible gust or a stream of smoke. It is an invisible torrent of ionized gas, mostly hydrogen and helium, but laced with heavier elements like nitrogen, carbon, and oxygen. This gas glows when excited by the star's ultraviolet radiation, producing the emission lines that astronomers study. But the wind itself is diffuse, spread thinly across enormous volumes of space. Even at the base of the wind, where the density is highest, the gas is far less dense than the best laboratory vacuum on Earth. It is only the staggering volume of space that the wind fills and the equally staggering duration over which it flows that makes the total mass loss significant. P Cygni's wind-blown nebula extends several light-years from the star. If you could somehow shrink our entire solar system, from the Sun out to the orbit of Neptune to the size of a dinner plate, The nebula of ejected material around P Cygni would stretch roughly 30 meters in every direction, a cloud of lost stellar material larger than any structure on Earth, generated by a single star that has been quietly bleeding into space for millions of years. The concept of stellar mass loss was not always understood. For most of the history of astronomy, stars were assumed to be essentially permanent objects. The ancient Greeks considered them fixed, eternal, and perfect. The medieval and Renaissance astronomers who inherited Greek cosmology saw the stars as unchanging beacons set into the celestial sphere. Even after the development of spectroscopy in the 19th century, which revealed that stars are made of the same elements found on Earth, the dominant picture was one of stability. Stars burned, stars shone, stars eventually died. But while they lived, they were assumed to be constant. The first theoretical hints that this picture might be incomplete came in the 1920s and 1930s. Sir Arthur Eddington, the British astrophysicist who had already proven Einstein's general relativity during the solar eclipse of 1919, turned his attention to the internal structure of stars. In 1926, Eddington published a calculation that would later become known as the Eddington luminosity, the maximum luminosity a star can sustain before radiation pressure begins to overcome gravity at its surface and drive material away. He showed that for stars above a certain mass threshold, roughly 100 to 150 solar masses, the radiation pressure alone would be sufficient to completely unbind the star. Nothing could hold it together. The light itself would tear it apart. No star above this limit could exist for more than a brief, violent moment before dissolving into an expanding cloud of luminous gas. But the Eddington limit described an absolute ceiling. Even stars well below this limit, stars with masses of 20 or 30 or 50 solar masses, could experience significant mass loss if conditions in their outer layers were favorable. The critical insight, developed over the following 5 decades by researchers including Subrahmanyan Chandrasekhar and later by Leon Lucy and Peter Solomon in the 1960s, was that the interaction between photons and atoms in a star's outer layers is not a simple, uniform process. Photons of specific wavelengths can be absorbed by specific atomic transitions, and when a photon is absorbed, its momentum is transferred to the atom. If the star has enough spectral lines, enough atomic transitions capable of absorbing photons at enough different wavelengths, the cumulative effect can produce a powerful outward wind. This mechanism, known as line-driven wind theory, was formally developed in its modern mathematical form by 3 American astrophysicists, John Castor, David Abbott, and Michael Klein, in a landmark paper published in 1975. Their framework, universally known as cake theory, after the author's initials, provided for the first time a quantitative predictive model for stellar wind mass loss rates. Given a star's luminosity, mass, radius, and chemical composition, Cygni theory could predict how fast the wind would blow and how much material it would carry away. It was a breakthrough of the first order. But the observational evidence for stellar mass loss predated the theory by centuries, and the single most important piece of that evidence came from P Cygni. P Cygni was first recorded as a new star in August of 1600 by the Dutch cartographer and astronomer Willem Janszoon Blauw. Working in the Netherlands at a time when European astronomy was still transitioning from the geocentric Ptolemaic model to the heliocentric Copernican framework, Blauw noted a star of approximately 3rd magnitude in the neck of Cygnus the Swan. 3rd magnitude is easily visible to the naked eye, bright enough to be noticed by anyone looking at the right patch of sky. Its absence from all previous star catalogues was unmistakable. Something new had appeared where nothing had been before. The star brightened somewhat over the following years, reaching perhaps 2nd magnitude before gradually fading. By 1626, it had dropped below naked eye visibility. It reappeared around 1655, brightened again, then faded once more. A 3rd and final brightening occurred around 1665, after which the star settled into a relatively stable state at approximately 5th magnitude, where it has remained, with minor fluctuations, for over 350 years. 5th magnitude is near the limit of what the unaided human eye can perceive. On a clear, moonless night, From a dark site far from city lights, you can see it. Barely. A faint point among thousands. This behavior was deeply puzzling to the astronomers of the era. Classical novae, the sudden brightening of faint or invisible stars, typically brightened once and then faded permanently. They were one-time events. P Cygni's repeated eruptions and recoveries did not fit this pattern. It was behaving like no known stellar phenomenon, and no one had the theoretical tools to explain it. It was not until the 20th century that astronomers began to classify P Cygni correctly. It was a luminous blue variable, a class of massive star that undergoes dramatic but non-terminal eruptions driven by instabilities in the radiation-gravity balance. These eruptions are not nuclear explosions. They are episodes of catastrophically enhanced mass loss, during which the star sheds enormous quantities of its outer layers before settling back into a quieter state. The cause of these eruptions, the precise trigger that pushes the star from stability into convulsion, remains debated to this day. But the most lasting contribution of P Cygni to astrophysics was not its eruptions, it was its spectrum. When astronomers first obtained detailed spectra of P Cygni in the late 19th century and the early decades of the 20th, they found something no one had seen before. Each emission line in the spectrum was accompanied by a blue-shifted absorption feature on its shorter wavelength side. The pattern was distinctive. A dark absorption trough shifted toward the blue, followed by a bright emission peak shifted slightly toward the red. This indicated that the gas around P Cygni was not static. It was moving outward, away from the star, at high speed, and the spectral signature of that motion was unlike anything produced by a stationary atmosphere. The physics behind this pattern is beautifully simple. The emission comes from the entire expanding wind, from gas moving in every direction around the star. Some of that gas moves toward us, some moves away, some moves perpendicular to our line of sight. All of it contributes to a broad emission feature centered near the rest wavelength of the spectral line. But the absorption comes from only one specific region, the gas that lies directly between us and the star, the gas moving toward us along our line of sight. This gas absorbs photons from the star's continuous background radiation at a wavelength shifted toward the blue because of the Doppler effect. The result is a unique spectral fingerprint, a blue-shifted absorption trough beside a red-shifted emission peak. This signature became known as the P Cygni Profile. It was the first direct spectroscopic evidence that a star was actively losing mass through an outflowing wind, and it was destined to become one of the most widely used diagnostic tools in all of astrophysics. The depth of the absorption trough reveals the column density of material in the wind. The velocity offset of the absorption minimum reveals the wind's terminal speed. The shape of the emission component reveals the geometry and density structure of the outflow. In a single spectral feature, the essential physics of a star's mass loss is encoded. A P Cygni profile is a star's confession, written in wavelengths of light, that it cannot hold onto its own material. If a grain of sand represented a single atom in P Cygni's stellar wind, then the total number of atoms being ejected from the star in a single year would fill thousands of football stadiums from floor to ceiling. The mass being shed is staggering, even by the profligate standards of stellar physics. Yet for centuries, it was invisible. Only when astronomers learned to spread the star's light into a rainbow of wavelengths, to read the dark and bright lines inscribed in that rainbow, did the truth become clear. P Cygni was not merely shining, it was bleeding. The P Cygni profile has since been found everywhere astronomers have looked, in hundreds of massive stars across the Milky Way, in stars in the Large and Small Magellanic Clouds, in supergiants in the Andromeda Galaxy, in the expanding shells of Type II supernovae during the first weeks after explosion, in the broad absorption line, outflows of quasars, powered by supermassive black holes billions of light-years away, even in the bipolar jets of newly forming protostars, still gathering material from their birth clouds. The spectral signature that was first identified in the light of a single flickering star in the constellation Cygnus turned out to be a universal fingerprint of matter in motion, a cosmic shorthand for the process of outflowing mass loss that operates at every scale, in every epoch, throughout the observable universe. P Cygni gave us more than a name. It gave us a language. a grammar for reading the winds of the cosmos, a way to measure the invisible, a way to see the slow unraveling of a star. The importance of this tool cannot be overstated. Before the P Cygni profile was understood, detecting stellar winds was extraordinarily difficult. Winds are transparent. They do not block the star's light in the way a solid object would. They do not produce obvious visual changes in the star's appearance. The only way to detect them is through their subtle effects on the spectrum, effects that require both high-resolution instrumentation and a clear theoretical framework for interpretation. The recognition of the P Cygni profile provided exactly that. It gave astronomers a reliable, repeatable quantitative method for identifying outflowing gas, measuring its speed, and estimating its density. Without it, our understanding of stellar mass loss would be decades behind where it is today. The star P Cygni itself sits at a distance of roughly 6,000 light-years from Earth, deep within the Cygnus arm of the Milky Way. This means that the light we see from P Cygni tonight left the star around 4,000 years before the Common Era, roughly contemporaneous with the construction of the earliest Egyptian pyramids. The eruption of 1600 that Blio recorded was itself an event that occurred around 4,400 years before his time. Every observation we make of P Cygni is an observation of the deep past, a fact that adds a peculiar poignancy to the study of its mass loss. We are watching a star bleed, but the blood we see was shed millennia ago. But here's the problem. Understanding that stars lose mass was only the beginning. The deeper question, the one that has driven decades of research and remains only partially answered, is a question of precision. How much mass do they lose? Why does the rate vary so dramatically from star to star and from epoch to epoch within a single star's life? And what are the consequences of getting the answer wrong? Because the process of stellar mass loss is not smooth, it is not predictable, it is not fully understood, and the consequences of miscalculating it ripple through every branch of modern astrophysics, from the formation of black holes to the chemical evolution of galaxies, to the origin of the elements in our own bodies. What scientists discovered as they dug deeper into the problem was that mass loss does not simply reduce a star's weight, it changes everything. It alters the star's evolutionary path through the Hertzsprung-Russell diagram, the fundamental chart that astronomers use to classify stars by their temperature and luminosity. It changes the star's internal structure, peeling away layers and exposing deeper, hotter, more chemically processed material. It modifies the star's surface chemistry, bringing to the surface elements that were forged deep in the core. It affects the star's rotation, because angular momentum is carried away with the departing mass. It determines the type of supernova the star will eventually produce, and it dictates the nature of the compact remnant left behind, whether a neutron star or a black hole. Every one of these consequences has implications that reach far beyond the individual star. The type of supernova affects the energy deposited into the surrounding interstellar medium. The chemical yields affect the composition of future generations of stars and planets. The mass of the remnant affects the gravitational wave signals produced when compact objects merge. The rotation of the stripped core affects the possibility of gamma-ray bursts, the most energetic explosions in the universe. Mass loss is not a footnote in stellar physics. It is the central narrative. And the star that taught us to read that narrative was P Cygni, quietly undressing in the darkness of the Milky Way, its spectral lines whispering the truth to anyone patient enough to listen. Then something happened that changed everything. The central problem with stellar mass loss is deceptively simple to state and enormously difficult to solve. The problem is this: the rate at which a massive star loses its outer layers determines almost everything about its future. It determines whether the star will end its life as a black hole or a neutron star. It determines the type, energy, and chemical yield of the supernova explosion at the end. It determines how much heavy material, the carbon, oxygen, nitrogen, iron, and all the other elements essential for rocky planets and living organisms, gets distributed into the surrounding interstellar medium. It determines the star's trajectory across the Hertzsprung-Russell diagram, the master chart of stellar properties. It determines the star's surface temperature, its radius, its spectral appearance, and its interaction with any companion stars in a binary system. And yet, despite more than half a century of dedicated theoretical and observational work, we still cannot predict stellar mass loss rates from first principles with anything close to the precision we need. To understand why this is such a hard problem, we need to look more closely at what happens inside a massive star and why the balance between gravity and radiation is so much more precarious than it first appears. Consider a star of 30 solar masses, roughly the size of P Cygni at birth. In its core, nuclear fusion is converting hydrogen into helium at a furious rate. The temperature at the center exceeds 40 million degrees Celsius, roughly 7 times hotter than the center of our own sun. At these staggering temperatures, the photons produced by fusion carry enormous energy. They do not travel in straight lines from the core to the surface. Instead, they ricochet through the dense core material, bouncing from atom to atom in a random walk. A drunkard stagger through a crowd of particles so thick that the average photon takes somewhere between 10,000 and 170,000 years to make the journey from center to surface. Each collision absorbs and re-emits the photon, transferring energy and momentum in a slow, grinding process that converts the gamma rays of fusion into the visible light and ultraviolet radiation that we ultimately observe. But when these photons finally reach the outer layers of the star, something important changes. The outer layers are not as dense as the core. The atoms there are more widely spaced, and many of them are partially ionized, meaning they have lost some of their electrons and are especially capable of absorbing photons at specific wavelengths. When a photon strikes one of these atoms at just the right wavelength, it can be absorbed. And when the photon is absorbed, its momentum, the tiny push it carries in the direction of its travel, is transferred to the atom. That atom is now moving slightly faster outward. If enough photons strike enough atoms, if the total momentum transferred outward exceeds the gravitational pull inward, the cumulative effect is a wind, a steady outflow of material leaving the star's surface and streaming into space. This is the line-driven wind mechanism that Castor, Abbott, and Klein formalized in their 1975 paper, the framework known as CK theory. The key insight of cake theory is that the acceleration of the wind is not driven by the total radiation output of the star. It is driven by the radiation absorbed in spectral lines. These are the narrow wavelength ranges where specific atoms, particularly the ions of iron, carbon, nitrogen, oxygen, silicon, and other metals, are especially efficient at capturing photons. In a hot star with a surface temperature of 20,000 to 30,000 degrees Kelvin, there are literally millions of these spectral lines. Each one is a tiny channel through which photon momentum can be funneled into the wind. Individually, each line contributes a small force. Collectively, they produce a torrent. Cake theory introduced a clever mathematical simplification. Rather than computing the force from every individual spectral line, a task that would have been computationally impossible in the 1970s, they parameterized the cumulative line force using a power law function called the force multiplier. This function describes how the total line force depends on the velocity gradient in the wind, which determines how many spectral lines are available to absorb photons at any given point. The result was a set of analytical equations that could be solved to predict the mass loss rate and terminal velocity of the wind, given only the star's basic properties. And for many stars, the theory worked. Cake predictions matched the observed mass loss rates for luminous O-type and early B-type stars within factors of 2 to 3. The predicted terminal velocities, typically between 1,000 and 3,000 kilometers per second, for the hottest stars, were in reasonable agreement with the blue-shifted absorption edges measured in observed P Cygni profiles. For the first time, stellar winds were not mysterious. They were the predictable, calculable consequence of radiation interacting with matter. The problem appeared to be solved, but then astronomers looked more carefully, and the cracks began to appear. The first major problem was the so-called weak wind problem. For stars at the lower end of the O-type range, with luminosities around 100,000 times that of the Sun, the observed mass loss rates fell significantly below CAK predictions. In some cases, The observed rates were 10 times lower. In a few cases, they were 100 times lower. The winds were there. Spectral signatures confirmed their existence, but they were far weaker than theory said they should be. Something was suppressing them, throttling the wind-driving mechanism, and no one could fully explain what. This was not a trivial disagreement. If the weak wind problem were confined to a handful of peculiar stars, it could be dismissed as a curiosity. But it affected an entire class of objects, a significant fraction of all O-type stars. And it raised an uncomfortable question. If CAC theory was wrong for these stars, how confident could we be that it was right for any of them? The second problem was far more dramatic. For the most luminous and most massive stars, the stars at the very top of the mass function, the observed mass loss rates were not lower than predicted. They were higher, sometimes spectacularly higher. P Cygni itself illustrates this. Its steady-state wind mass loss rate is already near the upper end of what line-driven wind theory predicts. But during its eruptive episodes, such as the one observed in 1600, the mass loss rate can spike to 100 or even 1,000 times the quiescent value. Material is ejected, not in a gentle breeze, but in massive eruptions, hurling solar masses of material into space in years rather than centuries. The wind becomes a flood, and it gets worse. P Cygni is not even the most extreme case. That distinction belongs to Eta Carinae, another luminous blue variable, located in the southern hemisphere sky at a distance of roughly 7,500 light-years. In 1843, Eta Carinae underwent a colossal eruption known as the Great Eruption. During this event, which lasted roughly 20 years, Eta Carinae briefly became the second brightest star in the entire night sky and ejected somewhere between 10 and 40 solar masses of material. The ejected material formed the spectacular homunculus nebula, a bipolar cloud of gas and dust visible in telescopes today, stretching roughly 1 light-year from end to end. This was not a supernova. The star survived. It is still there, but the amount of mass lost was comparable to throwing away an entire small star's worth of material in a cosmic blink of an eye. Sake theory cannot explain events like these. Line-driven winds, no matter how efficient, cannot produce mass loss rates of a solar mass per year. The numbers do not work. The force multiplier saturates. The wind becomes optically thick. The entire framework breaks down. Something fundamentally different must be at work during these eruptions. And identifying that something is where the problem becomes genuinely difficult. Several mechanisms have been proposed to explain the enhanced mass loss seen in luminous blue variables like P Cygni and Eta Carinae. Each has strengths, each has weaknesses. None is fully satisfactory. One leading hypothesis involves super-Eddington winds. Recall that the Eddington luminosity is the point at which radiation pressure exactly balances gravity at the star's surface. If a star's luminosity exceeds this limit, even temporarily, the radiation force on the outer layers becomes stronger than gravity, and material is blown off. During an LBV eruption, the luminosity may spike above the Eddington limit due to instabilities deep in the stellar interior. These instabilities could be triggered by changes in the opacity of the outer layers, changes in the nuclear burning rate in the core or in surrounding shells, or changes in the convective energy transport within the stellar envelope. A second proposed mechanism involves strange mode oscillations, a type of pulsation that arises specifically in the envelopes of very luminous stars. These oscillations are driven by the iron opacity bump, a region in the stellar envelope at temperatures around 150,000 to 200,000 degrees Kelvin, where iron and iron group elements are in a state of partial ionization that makes them extraordinarily efficient at absorbing radiation. This iron opacity peak acts like a valve, trapping radiation behind it, allowing pressure to build, and then releasing it in a violent pulsation that drives material off the star's surface. These pulsations can be violent enough to eject significant amounts of mass in short bursts, potentially explaining the irregular eruptions observed in LBV stars. A third possibility, still actively debated, is that some LBV eruptions are driven not by radiation at all, but by explosive energy release from nuclear burning instabilities. In the late stages of a massive star's life, nuclear burning can occur in multiple shells surrounding the core. with different nuclear fuels igniting at different depths. If one of these shells ignites suddenly or burns more rapidly than expected, the energy released can temporarily overwhelm the star's ability to radiate it away, leading to a surge of energy that inflates the envelope and drives Mossaf off the surface. Some models suggest that the violent ignition of a helium-burning shell, or instabilities associated with the pair instability mechanism in the most massive stars, could produce eruptions comparable to those observed in Eta Carinae. A fourth line of investigation focuses on binary interactions. Many massive stars, perhaps most, exist in binary or multiple systems. If a massive star has a close companion, gravitational interactions between the two can trigger mass transfer, tidal distortions, and even mergers that produce sudden, dramatic mass loss events. Some researchers have proposed that the great eruption of Eta Carinae was triggered not by an internal instability, but by a close encounter or merger with a companion star. The evidence is circumstantial but intriguing. Eta Carinae is known to be a binary system today, with a massive companion in a highly eccentric 5.5-year orbit. Whether this companion played a role in the Great Eruption remains an open question. The honest truth is that we do not fully understand what causes LBV eruptions. We can observe the results. We can measure the mass loss rates. We can map the expanding nebulae of ejected material. We can characterize the spectral changes that occur during and after an eruption. But the trigger mechanism, the precise reason why a star that has been stable for thousands of years suddenly ejects a significant fraction of its own mass in a matter of decades, remains one of the outstanding unsolved problems in stellar astrophysics. And the consequences of this uncertainty are profound, reaching far beyond the individual stars involved. To appreciate just how far-reaching the consequences are, consider a thought experiment. Take two identical stars, both born with exactly 40 solar masses, both with the same initial chemical composition, both rotating at the same rate, both formed at the same time in the same molecular cloud. The only difference between them is their mass loss history. Star A experiences strong, sustained, wind-driven mass loss throughout its life, losing a total of 20 solar masses before the end. Star B experiences weaker winds and fewer eruptions, losing only 8 solar masses. By the time they reach the end of their nuclear-burning lives, roughly 4 to 5 million years after their births, these two stars are radically different objects. Star A, having lost 20 solar masses, has a core of roughly 15 to 18 solar masses. It has been stripped down to its helium-rich layers. Its surface composition is dominated by helium and nitrogen, the products of the CNO cycle. It looks like a Wolf-Rayet star, hot and compact and furiously luminous. When it dies, it will likely produce a type Ib or icy supernova, an explosion with no hydrogen in its spectrum, because all the hydrogen was blown away decades or centuries before the final collapse. The compact remnant it leaves behind will likely be a neutron star, with a mass of roughly 1.4 to 2 solar masses. Star B, having lost only 8 solar masses, still retains a substantial hydrogen envelope. Its core is more massive, perhaps 20 to 25 solar masses. When it dies, it may produce a Type II supernova with prominent hydrogen lines, or it may collapse directly into a black hole with little or no visible explosion at all. The remnant it leaves behind could be a black hole of 10 to 15 solar masses, an object that might one day merge with another black hole and produce a gravitational wave signal detectable from billions of light-years away. Same initial conditions, different mass loss, entirely different outcomes. The type of supernova, the chemical yield, the mass and nature of the remnant, even the gravitational wave signal it might produce millions or billions of years later when it merges with a companion, all of these are determined by how much mass the star lost during its life, and we cannot predict that number reliably. Consider the endpoint of stellar evolution more broadly. A star's final fate, whether it becomes a white dwarf, a neutron star, or a black hole, depends critically on the mass of its core at the moment of death, and the mass of the core depends on how much mass the star has lost over its lifetime. A star that begins its life with 40 solar masses, but loses 20 solar masses through winds and eruptions, will have a very different core mass at death than an identical star that only loses 5 solar masses. The first star might end as a neutron star, its core compressed to nuclear density, spinning rapidly and emitting beams of radiation. The second might form a black hole, its core collapsing past the neutron star limit into a singularity wrapped in an event horizon. Same initial mass, same nuclear fuel, same basic physics, different mass loss history, completely different end. This means that our ability to predict the final fates of massive stars depends directly on our ability to model their mass loss accurately. The populations of neutron stars and black holes in the galaxy, the rates of supernovae of different types, the chemical yields of stellar deaths, all of these depend on getting the mass loss history right. And right now, we cannot. The problem extends far beyond individual stars. Massive stars are the engines of galactic evolution. Their winds inject energy and momentum into the interstellar medium, carving out bubbles of hot, low-density gas that shape the structure of star-forming regions across scales of hundreds of light-years. Their supernovae distribute heavy elements across vast volumes, enriching the raw material from which future generations of stars and planets will form. Their ultraviolet radiation ionizes the surrounding gas, creating expanding regions of hot plasma known as HII regions that dominate the visible structure of spiral galaxies. Every one of these processes depends on the mass and energy output of massive stars, and the mass and energy output depend on the mass loss history. If we underestimate mass loss rates, we overestimate the mass of stellar cores at death. This means we predict too many black holes and too few neutron stars. We undercount the enrichment of the interstellar medium during the star's wind phase. We miscalculate the mechanical energy deposited by the wind into the surrounding gas. The errors are not random, they are systematic. They propagate through our models at every level, from individual stellar evolution tracks to population synthesis codes that model the entire stellar content of a galaxy. Consider what this means for our understanding of chemical evolution. The Milky Way has been forming stars for roughly 13 billion years. Over that time, successive generations of massive stars have lived, shed mass, and died, each generation enriching the interstellar medium with heavier elements. The ratio of different elements in the interstellar medium today, the relative abundances of carbon, nitrogen, oxygen, iron, and dozens of other elements, is the cumulative result of 13 billion years of nucleosynthesis and mass loss. Models of galactic chemical evolution attempt to reproduce these observed abundances by tracking the contributions of stars of different masses, metallicities, and evolutionary stages over cosmic time. These models are only as good as their input physics, and one of the most critical inputs is the mass loss rate prescription used for massive stars. Different prescriptions produce different abundance patterns. Different abundance patterns lead to different conclusions about the history of star formation in the galaxy, the initial mass function, and the relative importance of different nucleosynthetic channels. A systematic error in mass loss rates can masquerade as a change in the star formation history, or as a different initial mass function, or as a need for exotic nucleosynthetic processes that may not actually exist. This is why the mass loss problem is not merely a specialist concern. It touches everything. It affects our interpretation of stellar populations in distant galaxies. It affects our estimates of the rate of Type Ia supernovae, which are used as cosmological distance indicators. It affects our understanding of the cosmic budget of metals, the elements heavier than helium that make up rocky planets and living organisms. It even affects our models of the reionization of the universe, the epoch roughly 800 million years after the Big Bang, when the first stars and galaxies produced enough ultraviolet radiation to ionize the intergalactic medium. The number and properties of those first ultraviolet sources depend on the mass loss rates of the first massive stars, which formed in an environment with essentially zero metallicity and therefore experienced very different wind-driving conditions than the stars we observe today. If we overestimate mass loss rates, the errors reverse. We predict too many neutron stars and too few black holes. We overcount the wind phase enrichment and undercount the supernova enrichment. The chemical evolution models shift. The predicted rates of gravitational wave events change. The entire framework tilts. Something is wrong with our assumptions. Not entirely wrong. Not catastrophically wrong, but persistently, stubbornly, consequentially wrong. The theoretical mass loss rates do not match the observed rates across the full range of stellar masses, luminosities, and evolutionary stages. The eruptions are essentially unpredictable. The clumping of stellar winds introduces systematic uncertainties into every mass loss rate derived from spectral observations, and the role of binary interactions, which can dominate the mass loss budget for a significant fraction of massive stars, is only beginning to be incorporated into population synthesis models. The clumping problem deserves special attention because it affects P Cygni directly. High-resolution spectroscopic monitoring of P Cygni over the past several decades has revealed that its wind is not smooth. It is lumpy, inhomogeneous, structured. The absorption trough of its P Cygni profiles varies on timescales of days to weeks, deepening and shallowing as denser clumps of wind material pass through the line of sight. These clumps, sometimes called wind blobs, are not minor perturbations. They are a fundamental feature of the wind's structure, predicted by theory and confirmed by observation. The line deshadowing instability, first identified in theoretical work by Stan Overkey and colleagues in the 1980s and 90s, shows that line-driven winds are intrinsically unstable. A small perturbation in the wind, a region moving slightly faster than its surroundings, is exposed to more unattenuated radiation from below because the spectral lines in the material behind it are Doppler shifted out of the way. This extra radiation accelerates the perturbation further, which exposes it to even more radiation, creating a runaway feedback loop. The result is a wind that spontaneously breaks up into dense shells and clumps, separated by regions of high-speed, low-density flow. The structure is chaotic, time-variable, and three-dimensional. This clumping has severe consequences for mass loss rate estimates. Most spectral diagnostics of stellar winds, including the strength of emission lines, the depth of P Cygni absorption troughs, and the intensity of free radio emission, depend on the density of the wind. But they depend on the density in different ways. Emission processes typically scale as the square of the density. If the wind is clumpy, with material concentrated in dense knots, the same total mass flux produces stronger emission than a smooth wind would. This means that smooth wind models, applied to a clumpy wind, will overestimate the mass loss rate because they need more total mass to explain the observed emission. When clumping corrections are applied to mass loss rate estimates for O-type stars and Wolf-Rayet stars, the derived rates typically decrease by factors of 2 to 4. In some cases, the reduction is even larger. This is not a minor adjustment. A factor of 3 reduction in the mass loss rate, sustained over a star's entire main sequence lifetime of several million years, translates to a difference of several solar masses in total material lost. That is enough to change the star's final fate, enough to flip the outcome from neutron star to black hole, or from a spectacular supernova to a quiet collapse. The Hubble Space Telescope has observed P Cygni and its surrounding nebula in exquisite detail, revealing the structure of the ejected material at wavelengths from the ultraviolet through the near-infrared. Ultraviolet observations have probed the ionization state and velocity structure of the inner wind, mapping the flow from the stellar surface outward. Optical narrowband imaging has revealed the faint, extended nebula of material ejected during the 17th century eruptions, a ghostly shell expanding slowly away from the star. Infrared observations from the Spitzer Space Telescope and the Herschel Space Observatory have detected thermal emission from dust grains that formed in the cooling outflow, tracing the distribution of solid particles mixed into the gaseous wind. And radio observations with the Very Large Array have measured the free emission from the ionized wind at centimeter wavelengths, providing mass loss rate estimates that are independent of the optical and ultraviolet diagnostics. All of these observations converge on the same unsettling conclusion. P Cygni is a star in a state of ongoing, significant, and not fully predictable mass loss. Its wind is clumpy, its history includes violent eruptions, its current quiescent state may be temporary, and the physical mechanisms responsible for its behavior, while partially understood, remain stubbornly resistant to precise quantitative modeling. P Cygni is not alone in this. Every luminous blue variable shares these properties to some degree. Ejecting, another LBV in the Milky Way, has undergone multiple outburst cycles and is surrounded by a ring nebula of ejected material. The Pistol star, near the center of the galaxy, is one of the most luminous stars known and has shed at least 10 solar masses of material into its surrounding Pistol nebula. HD 168625, in the Large Magellanic Cloud, underwent a dramatic outburst in the 1990s, transitioning from a quiet blue supergiant to an eruptive LBV state in a matter of years. These are not rare exotic objects. They are critical junctures in the evolution of massives. Most stars that begin their lives with more than 25 or 30 solar masses probably pass through an LBV phase at some point, shedding significant amounts of mass in eruptions that last decades or centuries. This phase may be brief compared to the star's total lifetime, but the mass lost during it can exceed the total mass lost during millions of years of steady wind-driven mass loss. The eruptions, unpredictable and poorly understood as they are, may be the dominant mechanism of mass loss for the most massive stars in the universe. The study of these eruptions has become one of the most active areas of research in massive star physics. Time domain surveys, both ground-based and space-based, are now monitoring thousands of luminous stars in the Milky Way and nearby galaxies, watching for the telltale signs of an impending eruption. Slow brightening, spectral changes, increased infrared emission from photosphomation in the wind. The hope is that, by catching an eruption in its early stages, astronomers can characterize the trigger mechanism and the energy source in ways that have never been possible before. P Cygni itself is the subject of one of the longest-running spectroscopic monitoring campaigns in the history of astronomy. Since the 1980s, a dedicated group of observers including Nolan Walborn, Ottmar Stahl, and Christian Sturken, among others, have tracked the star's spectral variations with high resolution and high cadence. These observations have revealed a wealth of information about the structure and variability of the wind. The hydrogen alpha emission line, the strongest feature in P Cygni's optical spectrum, varies in strength and shape on timescales ranging from days to years. The variations are not periodic. They are irregular, stochastic, driven by the passage of individual clumps and density enhancements through the wind. On longer timescales, spanning decades, the overall brightness of P Cygni has been gradually increasing by a few hundredths of a magnitude per century. Whether this slow brightening is a precursor to a future eruption, a normal phase of the star's evolution, or simply a minor fluctuation, no one can say with certainty. The star also shows evidence of past eruptions beyond the ones recorded in the 17th century. Imaging of the faint nebula surrounding P Cygni has revealed multiple concentric shells of ejected material, suggesting that the star has experienced several distinct episodes of enhanced mass loss over the past several thousand years. Each shell represents a separate eruption, a burst of mass loss that added another layer to the expanding cloud of gas around the star. The outermost shell has a radius of several light-years and an estimated age of tens of thousands of years, suggesting that P Cygni has been episodically erupting for far longer than the recorded history of human astronomy. But here's what makes this truly terrifying. If the eruptions are the dominant mass loss mechanism, and if we cannot predict them, then our models of massive star evolution are built on a foundation of controlled ignorance. We can model the winds. We can parameterize them, calibrate them against observations, and plug them into evolutionary codes with reasonable confidence that the results will be approximately correct during the long, quiet phases of a star's life. But the eruptions are wildcards. They can change a star's mass by several solar masses in a period too short for the evolutionary models to resolve. They are, in effect, discrete events that punctuate the smooth evolution of a star's mass with sudden, dramatic drops that reshape everything that follows. It is as though we are trying to predict the course of a river over thousands of years, and we have good models for the steady flow of water through the riverbed, but we cannot predict when a dam will burst. The dam bursts are rare, they are brief, but they change the landscape permanently. After the flood, the river does not return to its previous course. It carves a new one. In massive star physics, The eruptions are the dam bursts. They change the mass, they change the surface composition, they change the radius and the temperature and the luminosity. They create nebulae that affect the star's interaction with its environment. And after the eruption subsides, the star resumes its evolution, but on a different track, with a different mass, heading toward a different endpoint. The models can describe the track, but they cannot predict when the track will suddenly shift. The challenges are compounded by the fact that massive stars are rare. In the Milky Way, there are perhaps 100 to 200 known O-type stars within 2,000 light-years of the Sun, and only a handful of confirmed luminous blue variables in the entire galaxy. The sample sizes are small, the statistics are poor, the eruptions are infrequent enough that we have detailed observations of only a few, and even those observations are limited by the historical circumstances under which they were made. The great eruption of Eta Carinae in the 1840s was observed with the technology of the mid-19th century. No spectra were taken, no photographs, only visual brightness estimates and a few sketches. The eruptions of P Cygni in the 17th century were recorded even more crudely, as naked-eye observations in an era before the telescope was widely used for stellar astronomy. This is the core problem. Not that we know nothing, we know a great deal. But what we do not know, what remains hidden behind the iron opacity bump and the clumpy winds and the unpredictable eruptions, is precisely the information we need most. The mass loss rate, at all times and at all evolutionary stages, for stars of all masses and all metallicities. That number, or rather that function of time and stellar properties, controls the chemical enrichment of galaxies, the populations of compact remnants, the rates of gravitational wave events, and the availability of the heavy elements from which planets and life are built. It is one of the most important quantities in astrophysics, and we do not have it nailed down. The quest to understand stellar mass loss has taken astronomers down at least 5 major avenues of investigation over the past half-century of dedicated research and observation. Each avenue has illuminated a different facet of the problem. Each has produced genuine insights, genuine progress, and genuine predictions that have been tested against the stubborn reality of what the stars actually do. And each, in its own way, has also revealed new limitations, new complications, and new reasons to suspect that the full picture is more complex than any single framework can capture. These are not idle theoretical exercises. They are the result of decades of observation, computation, and painstaking spectral analysis. And their collective conclusion is both impressive and humbling. We have learned an enormous amount about stellar mass loss, and we still do not have enough to close the books. The first and most fundamental approach is the line-driven wind theory we have already encountered. The CAC framework, developed by Castor, Abbott and Klein in 1975, was the first successful attempt to derive stellar mass loss rates from first principles. Given a star's basic properties, its luminosity, mass, radius, and the abundance of heavy elements in its atmosphere, say K-theory predicts the rate at which the wind carries material away and the terminal velocity that the wind reaches far from the star. It does this by computing the total force exerted on the wind by the absorption of photons in millions of spectral lines, using a parameterized force multiplier that captures the cumulative effect of all those lines in a single mathematical expression. The physics is elegant. Photons streaming outward from the stellar surface encounter atoms in the outer atmosphere. Each atom has its own set of spectral lines, wavelengths at which it is especially efficient at absorbing radiation. When a photon at one of these wavelengths strikes the atom, it is absorbed, and its momentum is transferred to the atom, accelerating it outward. The atom then re-emits a photon, but in a random direction. The net effect is an outward push. Multiply this by millions of spectral lines and by the trillions upon trillions of atoms in the stellar atmosphere, and the result is a powerful wind streaming into space. For many classes of hot luminous stars, cake theory works well. The predicted mass loss rates for main sequence O-type stars, ranging from roughly 10 to the -7 to 10 to the -5 solar masses per year depending on the star's luminosity, matched the observed rates within factors of 2 to 3. The predicted terminal velocities, typically between 1,000 and 3,000 kilometers per second for the hottest stars, agreed with the blue shifted absorption edges measured in P Cygni profiles. For the first time, stellar winds were not mysterious phenomena. They were predictable consequences of radiation interacting with matter in quantifiable ways. But as observations improved, driven by the launch of ultraviolet space telescopes like the International Ultraviolet Explorer in 1978 and the Hubble Space Telescope in 1990, the limitations of cake theory became increasingly apparent. The first crack was the weak wind problem, the discovery that lower luminosity O-type stars, those with luminosities below about 200,000 solar luminosities, have wind mass loss rates that are 10 to 100 times lower than Cake prediction. These stars have winds. The spectral signatures are there, but the winds are anemic, far weaker than the theory predicts. Several explanations have been proposed for the weak wind problem. One is that the winds of these stars are so tenuous that the spectral lines used to diagnose them become optically thin, meaning the diagnostics systematically underestimate the true mass loss rate. Another is that the ionization balance in these winds is different from what the models assume, causing the force multiplier to be lower than predicted. A third, more radical possibility is that the winds of these stars are not purely line-driven at all, but are influenced by additional physics such as magnetic fields or wave-driven mechanisms that are not captured in the Cake framework. None of these explanations is fully satisfactory. The weak wind problem remains open, and it serves as a reminder that even our most successful theory of stellar mass loss has blind spots. The second major avenue of investigation addresses the eruptive mass loss that Cake theory cannot explain at all. The giant eruptions of luminous blue variables, the events that can shed solar masses of material in years to decades, require a fundamentally different driving mechanism. The leading candidate is the super Eddington wind, a continuum-driven outflow that occurs when the star's luminosity temporarily exceeds the Eddington limit by a significant factor. In a normal stellar wind, the driving force comes from line absorption. In a super Eddington wind, the driving force comes from continuum absorption, the interaction of photons with free electrons through Thomson scattering. Thomson scattering is wavelength independent and operates on all photons equally. When the luminosity is high enough, the radiation force from Thomson scattering alone can exceed gravity, driving material off the surface in a dense, optically thick outflow. Nathan Smith and Stan Awocki developed detailed models of this process in the early 2000s, showing that super Eddington luminosities could drive mass loss rates of up to 1 solar mass per year, consistent with the values inferred for the great eruption of Eta Carinae. Their models predicted that during a super Eddington phase, the star would develop an extended, cool pseudo-photosphere, the apparent surface of the optically thick wind, at a radius much larger than the true stellar surface. The star would appear to have expanded and cooled, even though the true surface had not moved. The visual brightness would increase dramatically because the pseudo-photosphere emits primarily at visible wavelengths, whereas the true stellar surface emits mostly in the ultraviolet. This prediction matched the observations of Eta Carinae during its great eruption remarkably well. Historical records suggest that Eta Carinae's visible brightness increased by roughly 2.5 magnitudes, making it briefly the second brightest star in the sky. But the total bolometric luminosity, the energy output at all wavelengths, may not have increased nearly as dramatically. Much of the apparent brightening was a redistribution of energy from the ultraviolet into the visible, caused by the expansion and cooling of the pseudo-photosphere. The star was not necessarily producing more energy, it was packaging that energy differently. But the Super Eddington model raises more questions than it answers. The fundamental mystery is what causes the luminosity to spike above the Eddington limit in the first place. In a star with a stable, steadily burning core, the luminosity changes only on nuclear timescales, millions of years. Something must happen inside the star to produce a sudden surge of energy reaching the surface. And the candidates are numerous, debated, and difficult to distinguish observationally. One candidate is the iron opacity bump, that critical zone deep in the stellar envelope where iron group elements in a particular ionization state become extraordinarily efficient absorbers. At temperatures near 150,000 degrees Kelvin, the opacity of the stellar material rises sharply, creating a bottleneck for radiation trying to escape. This opacity peak can trap energy, building up radiation pressure behind it until the layers above become dynamically unstable and are blown outward. Models by Matteo Cantiello, Norbert Langer, and collaborators have shown that the iron opacity bump can drive violent instabilities in stellar envelopes near the Eddington limit. But the details depend sensitively on the treatment of convection, mixing, and radiation transport in these extreme conditions, processes that are themselves poorly constrained. Another candidate is gravity darkening and rotational instabilities. Massive stars often rotate rapidly, and rotation modifies both the effective gravity and the effective temperature across the stellar surface. A rapidly rotating star is cooler and less gravitationally bound at its equator than at its poles. If the rotation rate is high enough, the equatorial regions can approach the effective Eddington limit, even when the poles are well below it, leading to enhanced equatorial mass loss or even mechanical mass ejection through rotational instability. This mechanism has been invoked to explain the bipolar morphology of the homunculus nebula around Eta Carinae, which shows a clear equator-to-pole structure, consistent with latitude-dependent mass loss. A third candidate involves nuclear burning instabilities. In the late stages of a massive star's evolution, nuclear burning proceeds through a series of increasingly rapid and energetic phases, from hydrogen burning through helium, carbon, neon, oxygen, and silicon burning. The transitions between these phases can be abrupt, and the ignition of a new fuel source in a shell around the core can release a pulse of energy that propagates outward through the envelope. If this pulse is energetic enough, it can drive the outer layers of the star to expand violently, triggering an eruption. Some models suggest that the energy released during the neon or silicon burning phases, which last only years to days, can be sufficient to unbind part of the stellar envelope. The numbers are striking. The gravitational binding energy of a massive star's outer envelope, the energy required to eject, say, 10 solar masses of material from a 40 solar mass star, is roughly 10 to the 48 to 10 to the 49 ergs. For comparison, the total energy released by nuclear burning in the last few years of a massive star's life, as it burns through its successive fuel stages, can reach 10 to the 51 ergs or more. There is, in principle, more than enough energy available to drive even the most dramatic LBV eruptions. The question is not whether the energy exists. It is whether and how that energy can be channeled efficiently into the ejection of the outer layers rather than being radiated away at the surface. This is a problem of energy transport, and it is ferociously difficult. The timescales of nuclear burning, convective transport, and dynamical expansion are all different. The geometry is three-dimensional. The radiation field is not isotropic. The opacity is a complicated function of temperature, density, and composition. Even with modern supercomputers capable of trillions of operations per second, fully self-consistent, three-dimensional simulations of LBV eruptions are at the frontier of what is computationally feasible. Different research groups using different numerical methods and different physical approximations obtain different results. Convergence has not yet been achieved. The third major approach to understanding mass loss shifts attention to a different class of objects: the Wolf-Rayet stars. These are the stripped-down remnants of massive stars that have already lost their hydrogen-rich outer layers either through winds, eruptions, or binary interaction. What remains is the bare helium core, surrounded by a dense, fast wind that produces broad emission lines across the spectrum. Wolf-Rayet stars are, in a real sense, the end product of stellar mass loss. They are what you get after the process has done its work. The winds of Wolf-Rayet stars are among the most powerful in the universe. Their mass loss rates range from roughly 10 to the -5 to 10 to the -4 solar masses per year, and their terminal velocities can exceed 3,000 kilometers per second. Their spectra are dominated by broad, strong emission lines, many showing P Cygni profiles, indicating massive outflows. The study of these winds has provided critical tests of wind theory and critical constraints on the mass loss process. One of the most important findings from Wolf-Rayet wind studies is the pervasive role of clumping. As mentioned earlier, Wolf-Rayet winds are highly inhomogeneous, with dense clumps occupying only a small fraction of the total wind volume. The volume filling factor, the fraction of the wind occupied by dense material, is estimated at roughly 5 to 10% for most Wolf-Rayet stars. This means that 90 to 95% of the wind volume is nearly empty, with the mass concentrated in compact knots and filaments. When clumping corrections are applied to mass loss rate estimates derived from emission line strengths and radio free emission, the rates decrease by factors of 2 to 4. For some Wolf-Rayet stars, the reduction is even larger, approaching a factor of 10. This was a sobering realization for the field. Mass loss rates that had been used in stellar evolution models for decades were systematically too high by factors that were large enough to change the predicted outcomes of stellar evolution. The revision of Wolf-Rayet mass loss rates cascaded through the entire field. If Wolf-Rayet stars lose mass more slowly than previously thought, they retain more of their helium envelopes for longer. The evolutionary tracks that connect their progenitor O-type stars to the Wolf-Rayet phase must be revised. The transition from hydrogen-rich to hydrogen-poor occurs at a different stage, at a different luminosity, at a different effective temperature. The predicted lifetimes of Wolf-Rayet stars change. The expected number of Wolf-Rayet stars in a galaxy changes. The chemical yields change. The predicted properties of the supernovae they produce change. One correction to the mass loss rate ripples through the entire chain of reasoning, from the wind at the stellar surface to the supernova at the end, to the chemical composition of the next generation of stars. Closely related to the clumping problem is the challenge of directly observing wind structure. For most of the 20th century, stellar winds were studied almost exclusively through spectroscopy, which provides information about the integrated properties of the wind along the line of sight, but cannot resolve the wind spatially. The wind of a massive star at a distance of several thousand light-years subtends an angle far too small to be resolved by any single optical telescope. The wind is there, we can measure its effects, but we cannot see it. This began to change with the development of optical and infrared interferometry in the 1990s and 2000s. Interferometric techniques combine the light from multiple telescopes separated by tens to hundreds of meters, synthesizing an effective aperture large enough to resolve structures on the scale of a few milliarc seconds. For the nearest and most luminous massive stars, this is just barely sufficient to resolve the innermost regions of the wind, the acceleration zone where the wind transitions from subsonic to supersonic flow. The Very Large Telescope Interferometer, VLTI, operated by the European Southern Observatory in Chile, and the Center for High Angular Resolution Astronomy, CHARA, array in California, have both contributed to this effort, providing the first direct measurements of wind geometry and asymmetry in a handful of nearby supergiants and Wolf-Rayet stars. The results have been revelatory. In several cases, the winds of massive stars are not spherically symmetric as most theoretical models assume. They show evidence of flattening, likely due to rapid rotation, or of localized density enhancements, possibly associated with magnetic fields or large-scale convective motions in the stellar envelope. For the Wolf-Rayet star WR104, interferometric imaging revealed a remarkable pinwheel nebula, a spiral pattern of dust formed in the wind collision zone between the Wolf-Rayet star and its companion. The spiral structure rotates as the binary orbits, painting a luminous pattern in the sky that encodes information about the wind velocities, the orbital geometry, and the dust formation conditions with extraordinary precision. Spectropolarimetry has provided another window into wind structure. When light from a stellar wind is scattered by free electrons, it becomes partially polarized. If the wind is perfectly spherically symmetric, the polarization contributions from different parts of the wind cancel out, and the net polarization is zero. But if the wind is asymmetric, if it is denser along the equator than the poles, or if it contains large-scale clumps or spiral structures, the cancellation is incomplete and a net polarization signal emerges. By measuring how the polarization varies across spectral lines, observers can reconstruct the three-dimensional geometry of the wind in ways that ordinary spectroscopy cannot. Studies of P Cygni itself using spectropolarimetric techniques have revealed subtle asymmetries in its wind, suggesting that the outflow is not perfectly isotropic and may be influenced by the star's rotation axis or by localized surface activity. Time domain surveys have added yet another dimension. Modern all-sky surveys like the Zwicky Transient Facility, the All-Sky Automated Survey for Supernovae, and soon the Vera-C. Rubin Observatory's Legacy Survey of Space and Time monitor millions of stars continuously, detecting brightness variations on timescales from hours to years. For massive stars, these variations can reveal pulsations, eruptions, and wind variability that would have gone undetected in the era of targeted observations. Several LBV candidates have been discovered through these surveys, identified by their characteristic irregular brightness variations. And for known LBVs like P Cygni, continuous monitoring has revealed subtle photometric fluctuations that correlate with spectroscopic changes in the wind, providing clues about the connection between surface instabilities and mass ejection events. The computational dimension of the problem has evolved in parallel with the observational one. Early models of stellar winds were one-dimensional and steady state, treating the wind as a smooth, spherically symmetric outflow that does not change with time. These models were analytically tractable and provided the foundational understanding of wind driving that enabled the CK theory and its successors. But the real winds of massive stars are three-dimensional, time-dependent, clumpy, and turbulent. Modeling them requires numerical simulations that push the boundaries of modern computing. Radiation hydrodynamic simulations of line-driven winds, in which the equations of fluid dynamics are solved simultaneously with the equations of radiation transport, have been conducted by groups in Europe, North America, and Asia with increasing resolution and physical fidelity. These simulations confirm that the line deshadowing instability naturally produces dense clumps and rarefied voids in the wind, with density contrasts of factors of 10 to 100. They show that the wind structure is highly dynamic, with clumps forming, merging, and dissolving on timescales of hours to days. And they reveal that the effective mass loss rate in a clumpy wind can differ from the rate in a smooth wind by factors that depend on the details of the instability and the wind parameters in ways that are not easily captured by simple scaling relations. The challenge of extending these simulations to three dimensions and coupling them to models of the stellar interior is formidable. A fully self-consistent simulation would need to resolve the convective motions in the stellar envelope, the subsurface opacity peaks that may drive pulsations and instabilities, the transition from the nearly hydrostatic atmosphere to the supersonic wind, and the large-scale structure of the wind out to distances of hundreds or thousands of stellar radii. The range of spatial and temporal scales involved spans many orders of magnitude, from the subphotospheric convective eddies that may seed wind clumps to the outer reaches of the wind where it merges with the interstellar medium. No existing simulation captures all of these scales simultaneously. Instead, different groups focus on different regions and different physical processes, assembling a patchwork understanding that is slowly converging toward a complete picture. The fourth avenue of investigation is binary interaction, and it may be the most consequential of all. For decades, stellar mass loss was studied primarily in the context of single stars, with winds and eruptions as the only channels for removing material. But starting in the late 1990s and accelerating through the 2000s and 2010s, a growing body of evidence revealed that many, perhaps most, massive stars do not evolve in isolation. They have companions, close companions. The statistics are stark. Surveys by Hugh Sanna and collaborators, published in 2012, found that over 70% of O-type stars in the Milky Way are born in binary or multiple systems, and roughly one-third of these will undergo mass transfer during their lifetimes, a process in which material from one star flows through the inner Lagrange point, the gravitational saddle between the two stars, and falls onto the companion. This is a completely different mechanism of mass loss. It is not driven by radiation, It is not driven by instabilities. It is driven by the simple fact that the star has expanded beyond the gravitational boundary of its own Roche lobe, and its material is falling downhill toward its neighbor. Mass transfer in close binary systems can strip the primary star of most or all of its hydrogen envelope in a relatively short time, typically a few thousand to a few 100,000 years. The physics is straightforward, even if the details are complex. As the more massive star in a binary system evolves, its radius expands. At some point, the star's surface reaches the Roche lobe boundary, the invisible gravitational surface, beyond which material is no longer bound to the star, but is instead drawn toward the companion. Once this boundary is crossed, material begins to flow through the inner Lagrange point, forming a stream of gas that spirals onto the companion star or into an accretion disk surrounding it. The rate of mass transfer can be enormous. During the rapid thermal timescale mass transfer phase that occurs when the primary star first fills its Roche lobe, the transfer rate can reach 10 to the negative 3 to 10 to the negative 2 solar masses per year. This is orders of magnitude higher than even the most vigorous stellar winds. In a few tens of thousands of years, the primary can lose more than half its mass. The material either falls onto the companion, increasing its mass and luminosity, or is ejected from the system entirely through the outer Lagrange points, forming a common envelope or a circumbinary disk. The result is a hot, compact, helium-rich core that is spectroscopically and structurally indistinguishable from a Wolf-Rayet star produced by wind-driven mass loss. The surface composition is dominated by helium and nitrogen, the products of CNO cycle hydrogen burning that have been exposed by the stripping of the hydrogen-rich envelope. The wind from this stripped core produces broad emission lines, including P Cygni profiles, just as a wind-stripped single star would. From spectroscopy alone, you cannot tell the difference. The realization that binary stripping could produce Wolf-Rayet stars was not entirely new. It had been proposed as early as the 1967 by Kippenhahn and Weigert, and was developed further by Paczynski in the same era. But for decades it was considered a secondary channel, a supplement to the dominant role of stellar winds. The shift came when two developments converged. First, the downward revision of Wolf-Rayet wind mass loss rates due to clumping corrections made it harder to strip stars through winds alone. Second, the binary surveys by Sanna and colleagues revealed that the binary fraction among massive stars was much higher than previously assumed. These two facts together implied that binary stripping might not be a secondary channel at all. It might be the primary one. Consider what this means for population synthesis. Population synthesis codes are computational tools that model the evolution of entire stellar populations, tracking thousands or millions of individual stellar evolution tracks, and combining them to predict the observable properties of star clusters, galaxies, and gravitational wave sources. These codes use mass loss rate prescriptions as one of their most critical inputs. If those prescriptions are calibrated against a Wolf-Rayet population that was largely produced by binary stripping rather than wind-driven mass loss, the resulting prescriptions will overestimate the effectiveness of winds. The codes will then predict too much wind-driven stripping, producing too many Wolf-Rayet stars and too many stripped envelope supernovae relative to what would actually occur in a population of single stars. The implications cascade further. The rates of Type Ib and IC supernovae, the explosions of stars that have lost their hydrogen envelopes, depend directly on the fraction of massive stars that reach the Wolf-Rayet stage before death. If binary stripping accounts for a larger share of this transformation than winds, then the supernova rates will depend more strongly on the binary fraction and the orbital period distribution than on the wind mass loss rates. The chemical yields of massive stars will change, because the timing and amount of envelope loss affect which nuclear burning products are ejected into the interstellar medium and which are retained in the core, and the predicted properties of compact remnant populations, the masses and spins of neutron stars and black holes, will shift accordingly. This is why the binary channel cannot be treated as a minor correction. It may account for the majority of envelope stripping in massive stars, and incorporating it correctly into evolutionary and population synthesis models requires not only accurate mass loss rate prescriptions for single-star winds, but also accurate models of binary, orbital evolution, mass transfer stability, common envelope physics, and the long-term behavior of post-mass transfer systems. Each of these is a research field unto itself. Each carries its own substantial uncertainties. This does not mean that wind-driven mass loss is unimportant. The P Cygni profiles observed in apparently single massive stars confirm that winds are real and carry significant amounts of material. But if a significant fraction of Wolf-Rayet stars, perhaps even a majority, are produced by binary stripping rather than by wind-driven mass loss, then the mass loss rates we have inferred by fitting evolutionary models to the observed Wolf-Rayet population may be systematically too high. We may have been attributing to winds a transformation that was largely performed by companion stars. Disentangling the relative contributions of winds, eruptions, and binary interactions to the total mass budget of massive stars remains one of the central challenges of modern stellar astrophysics, requiring detailed observations of large samples, careful determination of binary status, and sophisticated population synthesis modeling that accounts for all three channels simultaneously. The fifth and most recent approach to the mass loss problem comes from an entirely unexpected direction: gravitational wave astronomy. When the Laser Interferometer Gravitational Wave Observatory, LIGO, detected its first signal on September 14, 2015, it opened a new window on the universe. That first signal came from the merger of two black holes, with masses of approximately 36 and 29 solar masses, producing a final black hole of about 62 solar masses, with roughly 3 solar masses of energy radiated away as gravitational waves. The masses were surprising. They were significantly larger than most of the stellar mass black holes previously identified through X-ray observations, which typically had masses in the range of 5 to 15 solar masses. Prior to the LIGO detection, the most massive stellar black hole confidently measured was in the X-ray binary Cygnus X1, with a mass of roughly 15 solar masses. The LIGO event shattered that ceiling. The formation of black holes as massive as 30 or 36 solar masses required progenitor stars that had retained a substantial fraction of their original mass at the end of their lives. They could not have experienced the strong wind-driven mass loss predicted by standard prescriptions for solar metallicity stars. Something was different. Either the progenitor stars formed in a low metallicity environment, where winds were naturally weaker, or our mass loss rate prescriptions for massive stars at all metallicities are systematically too high. Or perhaps both factors were at work simultaneously, conspiring to preserve stellar mass in ways that the standard models had not anticipated. Subsequent detections by LIGO Virgo and later the CAGRA detector have expanded the catalogue of binary black hole mergers to well over 100 events, with component masses spanning a remarkably wide range from a few solar masses to nearly 100. Some of the most massive components, with masses approaching 80 or even 90 solar masses, are extraordinarily difficult to explain with standard stellar evolution models, unless mass loss rates are significantly lower than the values that have been used in population synthesis codes for the past 2 decades. The tension between observed black hole masses and predicted mass loss rates has become one of the most active areas of debate in the field, with implications that extend far beyond gravitational wave astronomy into every corner of stellar astrophysics. The numbers make the problem concrete and unavoidable. If you reduce the wind mass loss rate for a 40 solar mass star by a factor of 3 over its entire main sequence and post-main sequence lifetime, the final core mass at death increases from roughly 12 solar masses to roughly 18 solar masses. That single change, a factor of 3 in the wind prescription, is the difference between a neutron star and a moderately massive black hole, the difference between two entirely distinct classes of compact remnant with radically different observational signatures. If you make the same deduction for a 60 solar mass star, the final core mass can increase from roughly 20 solar masses to over 30 solar masses, consistent with the heaviest black holes detected by LIGO in its first several observing runs. The mass loss rate is not a minor parameter. It is the hinge on which the entire population of compact remnants swings, the single input that most strongly determines the distribution of black hole masses across the universe. These gravitational wave constraints have injected new urgency and new precision into the mass loss problem. Every merger event, every measured mass, provides a data point that constrains the mass loss history of the progenitor star system. The relationship between the initial mass of a star and the mass of the black hole it leaves behind is mediated almost entirely by mass loss. Wind-driven mass loss during the main sequence and post-main sequence phases, eruptive mass loss during the LBV phase if one occurs, binary mass transfer if a close companion is present, and fallback during the supernova explosion itself all determine how much of the original stellar mass ends up inside the event horizon and how much is returned to the interstellar medium. As the catalogue of gravitational wave detections grows, the statistical constraints tighten. The mass distribution of black holes detected by LIGO and Virgo shows features, peaks and gaps and cutoffs that encode information about the mass loss processes that shaped the progenitor population. The upper mass gap, the apparent scarcity of black holes, with masses between roughly 60 and 120 solar masses, is predicted by pair instability supernova theory and provides a direct test of mass loss rates in the most massive stars. The lower boundary of this gap depends on how much mass a star retains at the end of its life, which depends on the integrated mass loss over its entire evolutionary history. Future gravitational wave detectors, including the planned Einstein telescope in Europe and Cosmic Explorer in the United States, will detect binary black hole mergers at much greater distances and with much higher precision. These next-generation observations will constrain the mass distribution of compact remnants across cosmic time from the nearby universe to the epoch when the first massive stars formed. This will provide unprecedented constraints on how mass loss rates vary with metallicity and redshift, closing one of the most important remaining gaps in our understanding. And so the five approaches converge on a single unifying theme: line-driven wind theory, refined over 5 decades but still incomplete; super Eddington eruption models, powerful but poorly constrained; Wolf-Rayet wind studies, revealing the pervasive importance of clumping; binary interaction, potentially dominating the mass loss budget for a majority of massive stars; and gravitational wave observations, providing entirely new constraints from the endpoint of stellar evolution rather than the beginning. Each approach has contributed genuine understanding. Each has exposed genuine limitations. And together, they paint a picture that is simultaneously inspiring and sobering. We understand the basic physics of stellar mass loss better than ever before. We have theoretical frameworks, observational diagnostics, and computational tools that would have been unimaginable 50 years ago. But the full, quantitative, predictive understanding that we need, the ability to take a star of given initial mass, composition, and rotation and predict its mass loss history from birth to death, remains beyond our current reach. P Cygni stands at the center of this convergence, not because it is the most extreme case, but because it was the first. The spectral signature that bears its name is still the primary observational tool for detecting and measuring stellar winds. The eruptions it displayed 4 centuries ago remain among the best documented cases of transient mass loss, and its continued existence as a relatively quiet but still actively mass-losing luminous blue variable makes it a real-time laboratory for testing theories of wind driving, envelope instability, and the slow march of a massive star toward its inevitable end. The difficulty of the problem should not obscure the scale of the progress. We are much closer to a complete picture than we were 30 years ago. But the last pieces of the puzzle, the ones that connect the clumpy winds to the unpredictable eruptions, to the binary interactions, to the final remnant masses, remain stubbornly elusive. The stars are complex, the physics is extreme, and the answers, when they come, will reshape our understanding of how the universe builds its contents from the raw materials of starlight and gravity. Beneath the technical challenges and observational uncertainties lies a deeper truth that is easy to overlook amid the equations and spectral diagnostics. Mass loss is not a flaw. It is not a failure of stellar structure. It is not a bug in the physics of how massive stars work. It is an essential feature of the universe's metabolism, the process by which the cosmos recycles its own material, builds complexity from simplicity, and transforms the primordial hydrogen and helium of the Big Bang into the rich periodic table of elements that makes planets, oceans, atmospheres, and living organisms possible. Every atom of carbon in your body was forged in the core of a massive star. Every atom of oxygen in the water you drink was synthesized through nuclear fusion at temperatures exceeding 1 billion degrees Kelvin. Every atom of iron in your blood was produced in the last seconds before a supernova explosion, or in the merger of neutron stars in a cataclysm of gravitational energy. But here is the critical point that is often missed in popular accounts of stellar nucleosynthesis. Synthesizing these elements inside a star is not enough. They must be delivered to the interstellar medium. They must escape the star's gravitational grip and spread across the galaxy before they can be incorporated into new stars, new planets, and new forms of matter. Creation without delivery is futile. Stellar mass loss is the delivery mechanism. Without it, the heavy elements produced inside massive stars would remain locked in their cores, buried forever inside neutron stars and black holes, inaccessible to the rest of the universe. The interstellar medium would remain chemically pristine, composed of nothing but hydrogen and helium. There would be no rocky planets, no liquid water, no complex molecules, no amino acids, no proteins, no life. Let that sink in. The process that is slowly dismantling P Cygni, the wind that is stripping material from its surface and scattering it across light years of interstellar space, is the same fundamental process that ultimately made the existence of Earth possible. The same physics that is destroying one star is building the conditions for everything that comes after it. The enrichment does not happen all at once. It occurs in two distinct phases, each with its own timescale, its own chemical signature, and its own consequences for the galaxy. The first is the wind phase, during which the star is alive and actively burning nuclear fuel in its core. During this phase, which for a star like P Cygni may last several million years, material from the star's outer layers is carried away by the stellar wind and deposited into the surrounding interstellar medium. This material is not simply a sample of the primordial gas from which the star formed. It has been processed. Convective mixing and rotational circulation dredge up material from the nuclear burning regions of the interior to the surface, gradually changing the surface composition over time. For massive stars in the later stages of their main sequence evolution, the surface can become enriched in nitrogen and helium, the products of the CNO cycle that converts hydrogen into helium while using carbon, nitrogen, and oxygen as catalysts. The wind carries this processed material outward, depositing it in the circumstellar environment at a steady rate measured in tens of thousandths of a solar mass per year. For P Cygni specifically, the wind is carrying away material at a rate of roughly 10 to the -5 solar masses per year. Over its remaining lifetime of perhaps a few 100,000 years, it will return several solar masses of nitrogen-enriched, helium-enriched material to the interstellar medium through this steady-state process alone. This is before any additional eruptive mass loss events which could contribute several more solar masses in short, violent bursts. The total mass returned during the wind phase, including both the steady wind and the episodic eruptions, could amount to 10 to 20 solar masses, a substantial fraction of the star's birth mass. The second phase is the supernova. When the star exhausts its nuclear fuel and its iron core collapses under its own gravity, the resulting explosion ejects the remaining outer layers at velocities of 5,000 to 30,000 kilometers per second. This explosion distributes a broader and richer range of heavy elements into the interstellar medium than the wind phase alone can provide. The supernova ejector contains significant quantities of carbon, oxygen, neon, magnesium, silicon, sulfur, calcium, and iron group elements, all synthesized during the successive nuclear burning stages in the star's interior, or in the explosive nucleosynthesis that occurs during the supernova shock itself. The relative contributions of the wind phase and the supernova phase to the total chemical enrichment depend critically on the star's mass loss history. This is one of the most important and least appreciated connections in stellar physics. A star that has lost most of its hydrogen envelope through winds and eruptions before the supernova will return more nitrogen and helium during the wind phase, but less heavy elements during the explosion, because the massive outer layers that would have been processed during the final burning stages have already been removed. The core is lighter, the explosion is different, the nucleosynthetic yields shift. Conversely, a star that retains most of its envelope until the supernova will distribute more of its processed material during the explosion itself. The heavier envelope means a more massive core at collapse, potentially a more energetic explosion, and a different distribution of elements in the ejector. In extreme cases, if the star retains so much mass that its core exceeds roughly 40 to 50 solar masses at death, it may collapse directly into a black hole without producing a supernova at all, swallowing its heavy elements forever. This is the failed supernova scenario, and it represents the ultimate failure of the delivery mechanism. The elements were synthesized but never delivered. This is why mass loss rates matter so profoundly for galactic chemical evolution. The balance between wind and supernova enrichment determines the chemical composition of the interstellar medium, which in turn determines the composition of the next generation of stars and planets. If mass loss rates are higher than we currently estimate, we would expect the interstellar medium to be more enriched in nitrogen and helium relative to heavier elements, because more processed material is expelled during the wind phase, while less remains for the supernova. If mass loss rates are lower, the enrichment pattern shifts toward more iron group elements from the supernovae of more massive cores. Observations of chemical abundances in nearby galaxies and in ancient metal-poor stars in the halo of the Milky Way provide constraints on these enrichment models, and the constraints are remarkably tight. The observed abundance patterns, the ratios of carbon to nitrogen, oxygen to iron, alpha elements to iron peak elements, and dozens of other elemental ratios measured in stars of different ages and locations, can only be reproduced by galactic chemical evolution models if the mass loss rates and supernova yields are within relatively narrow bounds. Getting the mass loss rates wrong by even a factor of 2 can produce abundance patterns that conflict with observations. The isotopic ratios of certain elements, such as the ratio of nitrogen-14 to nitrogen-15 or carbon-12 to carbon-13, are particularly sensitive to the details of wind enrichment from massive stars, providing forensic evidence of the mass loss rates in previous stellar generations. This is not science fiction. This is not abstract theory. This is the hard quantitative reality of how the universe builds its chemical inventory. And the signature that allows us to track this process, star by star, wind by wind, epoch by epoch, is the P Cygni Profile, the spectral fingerprint that P Cygni donated to astrophysics 4 centuries ago. Consider the broader canvas. The Milky Way contains roughly 200 to 400 billion stars. Of these, perhaps a few million at any given time are massive enough to drive significant stellar winds. These stars are concentrated in the spiral arms and star-forming regions of the galactic disk, where molecular clouds provide the raw material for ongoing star formation. At any given moment, these massive stars are collectively injecting material into the interstellar medium at a combined rate of roughly 1 solar mass per year across the entire galaxy. This may not sound like much, spread across a galaxy 100,000 light-years in diameter, but the cumulative effect over cosmic time is enormous. Over the roughly 13 billion-year history of the Milky Way, winds from massive stars have returned billions of solar masses of processed material to the interstellar medium. This material has been incorporated into successive generations of stars, each one slightly richer in heavy elements than the last. If you could compress the entire history of the Milky Way into a single calendar year, with the galaxy's formation at midnight on January 1st, and the present moment at midnight on December 31st, the Sun would have formed sometime in mid-September. By that point, roughly 8 to 9 billion years of stellar nucleosynthesis and mass loss had already occurred, enriching the solar neighborhood with enough heavy elements to form rocky planets, liquid water, and the complex organic molecules that are the precursors to life. The Sun itself is approximately a third-generation star, assembled from material that had already been processed through at least two previous cycles of star formation, nuclear burning, mass loss, and explosive death. The atoms in your body have been inside other stars before they were inside you. Let that sink in. P Cygni is participating in this cycle right now, at this very moment. Its wind is carrying helium, nitrogen, and traces of heavier elements outward from its surface, depositing them in the circumstellar medium where they will eventually merge with the general interstellar gas. When P Cygni finally explodes, probably within the next few 100,000 years, the supernova will distribute an even richer payload of heavy elements across tens of light years of space. And in the ruins of that explosion, new molecular clouds will form, new protostars will ignite, new planetary systems will condense from the enriched debris, perhaps a world with liquid water, perhaps a world with complex organic chemistry, perhaps a world where awareness emerges once again. There is another dimension to the deeper truth that is rarely discussed in popular treatments of stellar physics, but that profoundly shapes the structure of the galaxy we live in. Mass loss does not only affect the star that is losing mass, it affects the star's environment, its neighbors, and the architecture of the interstellar medium itself. The wind from a massive star creates a bubble of hot, low-density gas around the star, known as a wind-blown bubble. The physics is straightforward but dramatic. The fast stellar wind, moving at 1 to 2,000 kilometers per second, collides with the nearly stationary interstellar medium surrounding the star. The collision produces a shock wave that heats the gas to temperatures of millions of degrees, creating a hot, pressurized interior that expands outward, sweeping up the surrounding interstellar material into a dense shell. This wind-blown bubble can extend tens of light years from the star, carving out a cavity in the interstellar medium that fundamentally alters the environment in which the star exists, and will eventually die. When the star finally explodes as a supernova, the blast wave does not propagate into undisturbed interstellar gas. It propagates through the wind-blown bubble, the hot cavity carved out by millions of years of stellar wind activity. The interaction between the supernova remnant and the pre-existing bubble structure determines the morphology, evolution, and energy distribution of the remnant in ways that cannot be understood without accounting for the prior mass loss history. The supernova remnant is not a fresh imprint on a blank canvas. It is an overwriting, a new signature, scrawled across the record of everything the star has already done to its environment. In regions where many massive stars are concentrated, such as young stellar clusters and OB associations, the combined effect of multiple winds and supernovae can carve out enormous cavities in the interstellar medium, known as superbubbles. These superbubbles can reach diameters of hundreds or even thousands of light years and persist for tens of millions of years. They are among the dominant structures shaping the interstellar medium in star-forming regions of the Milky Way and other galaxies, and their properties, their sizes, their temperatures, their expansion rates, their chemical compositions, depend directly on the mass loss rates and wind properties of the massive stars driving them. The energy injected by stellar winds into the interstellar medium is not a minor perturbation. For a typical O-type star, with a mass loss rate of 10 to the negative 6 solar masses per year and a terminal wind velocity of 2,000 kilometers per second, the mechanical luminosity of the wind, the rate at which kinetic energy is deposited into the surrounding medium, is roughly 10 to the 36th ergs per second. Over the star's main sequence lifetime of a few million years, this amounts to roughly 10 to the 50th ergs of total mechanical energy input, a figure that is comparable to the kinetic energy released in a supernova explosion. In other words, the cumulative energy input from the wind over the star's entire life is as important, energetically, as the single cataclysmic explosive input at the end. This realization has transformed our understanding of the interstellar medium and the process of star formation itself. Stellar winds and supernovae do not simply destroy molecular clouds by disrupting them, they also compress them. The expanding shells driven by winds and supernova blast waves sweep up interstellar gas, piling it into dense layers. If these layers become dense enough, they can become gravitationally unstable, fragmenting and collapsing to form new molecular cloud cores, new protostars, new stellar systems. This process, known as triggered or sequential star formation, creates a self-perpetuating cycle that is one of the most beautiful feedback loops in astrophysics. Massive stars form from molecular clouds. Their winds and supernovae compress surrounding gas, triggering the formation of new massive stars, which in turn drive new winds and produce new supernovae, compressing more gas and triggering more star formation. The cycle has no obvious beginning or end. It has been running for billions of years, churning the interstellar medium, mixing in freshly synthesized heavy elements, and gradually increasing the complexity of the galaxy's chemical inventory with each generation. And at every stage, the rate of stellar mass loss sets the pace and the character of the cycle. Faster mass loss means stronger winds, larger bubbles, more energetic compression, more efficient triggering, and a higher rate of induced star formation. Slower mass loss means weaker feedback, smaller cavities, less compression, and a slower pace of galactic evolution. The mass loss rate of a single star is a small thing, measured in tenths of millionths of a solar mass per year, but multiplied across millions of massive stars over billions of years, it becomes one of the dominant forces shaping the structure and evolution of an entire galaxy. The connection between stellar mass loss and the large-scale structure of galaxies extends even beyond the galactic disk. In starburst galaxies, where star formation rates are tens to hundreds of times higher than in the Milky Way, the combined effect of millions of massive stellar winds and supernovae can drive galactic-scale outflows, enormous fountains of hot, chemically enriched gas that stream out of the galaxy's disk into the halo and beyond, sometimes escaping into the intergalactic medium entirely. These galactic winds, or superwinds, carry heavy elements far beyond the galaxy, enriching the intergalactic medium with carbon, oxygen, silicon, iron, and other products of stellar nucleosynthesis. The enrichment of the intergalactic medium has been observed directly through absorption lines in the spectra of distant quasars. As quasar light travels across billions of light-years of space, it passes through filaments and clouds of intergalactic gas. At each encounter, the gas imprints absorption lines on the quasar spectrum at wavelengths corresponding to the heavy elements it contains. The detection of carbon, silicon, and oxygen in intergalactic gas clouds far from any galaxy is direct, unambiguous evidence that stellar mass loss, amplified by supernova explosions and driven outward by galactic winds, operates on truly cosmic scales. The atoms ejected by individual stars like P Cygni are part of a process that enriches not just the immediate vicinity of the star, not just the galaxy in which it resides, but the entire intergalactic web. The consequences of this enrichment are visible in the structure of the Milky Way itself. There is a well-established metallicity gradient across the galactic disk. Stars and gas clouds nearer the galactic center have higher heavy element abundances than those in the outer disk. This gradient reflects the cumulative history of star formation and mass loss across the galaxy. The inner regions, where star formation has been more vigorous and more massive stars have lived and died, are more heavily enriched. The outer regions, where star formation has proceeded more slowly and fewer massive stars have contributed their yields, remain more metal-poor. The gradient is not sharp. It is smooth, measured at roughly negative 0.05 to negative 0.07 dex per kiloparsec, a gentle slope that encodes billions of years of chemical evolution, driven by the winds and explosions of massive stars. This gradient has practical consequences for the mass loss problem itself, creating a feedback loop of remarkable subtlety. Stars that form in the more metal-rich inner galaxy have stronger line-driven winds, because they have more metallic ions to absorb radiation and drive the outflow. Stronger winds mean more mass loss, which means more enrichment of the local interstellar medium, which means the next generation of stars forms with even higher metallicity and even stronger winds. Conversely, stars in the metal-poor outer disk have weaker winds, less enrichment, and a slower pace of chemical evolution. The mass loss rate is both a consequence of the galaxy's chemical state and a driver of its future evolution. The galaxy and its stars co-evolve, each shaping the other through the intermediary of stellar winds. This co-evolution extends across cosmic time. In the early universe, when the first galaxies were assembling from nearly pristine gas with metallicities less than 1% of the solar value, stellar winds were correspondingly weak. The first massive stars lost relatively little mass through line-driven winds, retaining more of their envelopes and producing more massive cores at death. This may explain why the earliest stellar black holes were so massive, as inferred from gravitational wave detections and from models of the earliest stages of galaxy assembly. As successive generations of stars enriched the interstellar medium, winds and strengthened, mass loss rates increased, and the typical remnant masses decreased. The population of compact objects evolved in lockstep with the chemical evolution of the galaxy, connected by the physics of radiation-driven mass loss. The observational evidence for this coevolution is growing. Studies of massive stars in environments of different metallicity, from the metal-rich inner Milky Way to the metal-poor Magellanic Clouds to extremely metal-poor dwarf galaxies in the local group, have confirmed that wind mass loss rates scale with metallicity approximately as predicted by line-driven wind theory, though the exact scaling exponent remains debated. Stars in the small Magellanic Cloud, with a metallicity roughly 1/5 of the Sun's, show mass loss rates roughly 3 to 5 times lower than comparable stars in the Milky Way's disk. This confirms the theoretical expectation and provides direct empirical calibration of the metallicity dependence that underpins all galactic chemical evolution models. From the surface of a single flickering star in the constellation Cygnus to the vast filaments of the cosmic web stretching across hundreds of millions of light years, the process of stellar mass loss connects the smallest scales of atomic physics to the largest structures in the observable universe. The photon that pushes an iron atom off the surface of P Cygni is the same fundamental interaction, the electromagnetic force coupling radiation to matter, that drives galactic-scale outflows and enriches the cosmos with the elements of life. The P Cygni profile, that distinctive spectral signature of blue-shifted absorption and red-shifted emission, is the observational thread that ties it all together, the diagnostic that allows us to detect and measure outflows at every scale, from stellar winds to galactic superwinds, to the outflows of active galactic nuclei powered by supermassive black holes. The deeper truth, then, is this. Stellar mass loss is not an isolated phenomenon. It is a link in a chain that connects the nuclear reactions in the cores of individual stars to the chemical composition of the universe as a whole. It is the mechanism by which the cosmos distributes the products of its own internal processes, spreading complexity outward from the points where it is generated, enabling the construction of increasingly elaborate structures, from atoms to molecules to minerals to worlds to living systems. It is, in the most literal sense, the process by which the universe gives itself away, in order to become something more than it was. And P Cygni, that restless, luminous, slowly disintegrating star in the northern sky, is one of its most eloquent examples. What does all of this mean for us, for humanity? For our understanding of where we came from and where we are going? The most immediate implication is humbling. We exist because stars die badly, not in the sense that they fail, but in the sense that their dying is messy, violent, and prodigiously generous. If massive stars were perfect objects, if they burned their fuel with flawless efficiency and collapsed cleanly into compact remnants without losing a single atom to the surrounding cosmos, the universe would be a sterile place. There would be hydrogen. There would be helium. There would be a scattering of lithium and beryllium left over from the first few minutes after the Big Bang. There would be darkness between the stars. And there would be nothing else. No worlds, no water, no carbon chemistry, no awareness. But stars are not perfect. They are imperfect in the most productive way imaginable. They leak, they erupt, they shed their outer layers. They throw their processed interiors into the void. And in doing so, they populate the cosmos with the raw materials for everything complex, everything interesting, everything beautiful. The imperfection is the point. P Cygni is one of those gloriously imperfect stars. Its inability to hold itself together, its compulsion to hurl matter into interstellar space at hundreds of kilometers per second, is not a defect. It is a contribution. Every atom it ejects is an atom that might, in a few million years, find itself incorporated into a new molecular cloud, a new protoplanetary disk, a new rocky world. The nitrogen in P Cygni's wind might one day be part of an amino acid on some distant planet. The helium might one day be part of a nebula so strikingly beautiful that some future species pauses to wonder at it. The carbon might become part of a cell membrane. The oxygen might become part of an atmosphere that something breathes. We are not separate from this process. We are products of it. The iron in the hemoglobin molecules that carry oxygen through your bloodstream was forged inside a star not unlike P Cygni, a massive, luminous, unstable giant that could not contain its own energy and its own material. That iron was ejected, either in a stellar wind or in a supernova explosion, dispersed into interstellar space, gathered by gravity into a collapsing molecular cloud, compressed into a rotating protoplanetary disk, accreted into a differentiated rocky planet, and eventually incorporated into the biology of an organism capable of reading about its own origins. The journey of a single iron atom from the interior of a massive star to a hemoglobin molecule in your blood spans billions of years, crosses thousands of light years, and passes through multiple generations of stars. It is one of the longest supply chains in the universe. If you trace the lineage of any atom in your body all the way back to its creation, you are tracing a journey that passes through at least 2 and possibly 3 previous stellar generations. Each generation burned brighter and died harder than its predecessor, each one contributing its processed material to the interstellar medium, each one raising the overall metallicity of the local galactic environment by a tiny but meaningful fraction. By the time the Sun formed, 4.6 billion years ago, the raw material in the solar neighborhood had been enriched to approximately 2% heavy elements by mass. Just 2%. That is the entire total legacy of roughly 8 to 9 billion years of stellar nucleosynthesis and mass loss, the accumulated yield of millions of massive stars that lived and died before our solar system existed. 2% may sound trivially small. It is not. That 2% was exactly enough. Enough for iron cores in terrestrial planets. Enough for silicate mantles and basaltic crusts. Enough for water molecules with their remarkable solvent properties. Enough for the carbon-nitrogen-oxygen chemistry that underlies all known biology. Enough for life. The difference between 2% and 0% is the difference between a universe of gas and darkness and a universe of worlds and light and conscious awareness. That slender 2% margin is maintained by stellar mass loss, the process that P Cygni embodies with such dramatic flair. There is a philosophical dimension here that is worth dwelling on for a moment. The universe has no obligation to be comprehensible. There is no law of physics that requires the products of stellar nucleosynthesis to assemble themselves into structures capable of understanding stellar nucleosynthesis. There is no cosmic mandate that says the carbon forge inside a red giant must eventually become part of a nervous system that can contemplate the life cycle of red giants. And yet here we are, made of star stuff, as Carl Sagan and others have famously observed, but more specifically, made of star stuff that was lost, ejected, stripped away. The matter that constitutes your body is matter that one or more stars could not hold on to. You are assembled from stellar discards. There is something both poignant and extraordinary about this realization. The universe did not have to produce observers. The strengths of the fundamental forces did not have to be tuned to allow stars to burn stably for billions of years while remaining unstable enough to lose mass and distribute their products. Nuclear physics did not have to produce carbon through the triple alpha process, with its fortuitous resonance, identified by Fred Hoyle in one of the great predictive triumphs of 20th century astrophysics. And massive stars did not have to lose mass at rates that happened to distribute heavy elements efficiently enough to produce rocky planets within a few billion years of a galaxy's formation. But all of these conditions are met in our universe, and the result is a cosmos that is not only vast and ancient and violent, but also, in at least one small corner, aware of itself and actively investigating the mechanisms of its own construction. Whether this awareness is rare or common, whether there are other worlds orbiting other stars where other forms of intelligence ponder the life cycles of massive stars, we do not yet know. The question remains one of the most profound in all of science, and the answer may not come in our lifetimes, or even in the lifetime of our civilization. but we do know that the process which made us possible is universal. It is not a local accident or a peculiarity of our galactic neighborhood. Stellar mass loss operates in every galaxy in the observable universe. The P Cygni profile has been observed in stars across the local group and beyond, in galaxies millions and even billions of light-years from Earth. The same physics that drives P Cygni's wind drives the winds of O-type stars in the Andromeda Galaxy, in the Triangulum Galaxy, in distant starburst galaxies, whose light left them when the universe was less than half its current age. The enrichment cycle operates everywhere. The delivery mechanism operates everywhere. The potential for complexity operates everywhere. This does not mean that life is everywhere. The gap between having the right elements available in the right proportions and having functioning, self-replicating biological organisms is enormous, and we do not yet understand in detail how it was bridged, even on our own planet. Abiogenesis, the origin of life from non-living chemistry, remains one of the great unsolved problems of science, a puzzle that sits at the intersection of chemistry, geology, biology, and planetary science. But the first prerequisite for life as we know it, the distribution of heavy elements into the interstellar medium in the right abundances, the right chemical forms, and the right spatial concentrations for rocky planet formation, is clearly met throughout the observable cosmos. The stars have done their part. They are doing their part right now. P Cygni is doing its part right now, shedding nitrogen and helium and traces of carbon and oxygen into the space around it, building the next generation's chemical inheritance one atom at a time, one wind-driven parcel at a time. There is a second, more practical implication that deserves attention, one that affects the daily work of thousands of astronomers and astrophysicists around the world. Our ability to understand the universe depends on our ability to model stellar mass loss correctly. This is not an exaggeration for dramatic effect. It is a literal description of the situation. The distances to galaxies, the ages of stellar populations, the predicted formation rates of black holes and neutron stars, the chemical evolution of the Milky Way and other galaxies, the interpretation of gravitational wave signals, the calibration of Type Ia supernova distances used to measure the accelerating expansion of the universe, and the nature of dark energy, all of these depend, directly or indirectly, on mass loss rate prescriptions embedded deep within our stellar evolution models. If those prescriptions are wrong, by even modest factors, the errors propagate outward through every dependent field of astrophysics. The inferred distances might shift. The estimated ages of globular clusters might change. The predicted merger rates of binary neutron stars might not match the rates inferred from gravitational wave observation. The galactic chemical evolution models might fail to reproduce the observed abundance patterns in metal-poor halo stars. The predicted ionizing photon output of massive star populations, which determines how and when the universe was reionized after the cosmic dark ages, might be off by factors large enough to matter. The entire edifice of modern astrophysics rests, to a degree that many people outside the field do not appreciate, on our understanding of how massive stars shed their outer layers. And as we have seen throughout this documentary, that understanding is still very much a work in progress. This is not a reason for despair or cynicism about the enterprise of astrophysics. It is a reason for continued, vigorous investigation, and it is one of the reasons why the study of stellar mass loss remains such an active and well-funded field of research. Every improvement in our mass loss rate prescriptions, every new observation of a stellar wind or an LBV eruption, every gravitational wave detection that constrains the masses of compact remnant progenitors, brings us closer to a complete and internally consistent picture of massive star evolution. The problem is genuinely hard, but the tools available for attacking it are getting better with each passing year and each new generation of instruments. The James Webb Space Telescope, operating at infrared wavelengths from its orbit at the second Lagrange point, is providing spectroscopic data of unprecedented sensitivity and resolution for massive stars in the Milky Way and in nearby galaxies, enabling more precise measurements of wind velocities, mass loss rates, and chemical abundances in environments spanning a wide range of metallicities. The extremely large ground-based telescopes currently under construction, the European Extremely Large Telescope in Chile, the 30-meter telescope in Hawaii, and the Giant Magellan Telescope also in Chile, will bring adaptive optics-corrected diffraction limit imaging and high-resolution spectroscopy to bear on individual massive stars in galaxies throughout the local group, resolving details of wind structure and stellar surface activity that are inaccessible to current facilities. The next generation of gravitational wave detectors, including the planned Einstein Telescope in Europe and Cosmic Explorer in the United States, will expand the catalogue of compact object mergers by orders of magnitude, detecting events at cosmological distances and providing statistical constraints on remnant mass distributions that encode the integrated mass loss histories of their progenitor populations across cosmic time. The star P Cygni will be there through all of it, still burning, still shedding material, still writing its spectral signature in the light it sends toward our telescopes. A 400-year-old laboratory for one of the most important unsolved problems in astrophysics, patiently waiting for us to develop the tools and the theoretical frameworks needed to read its message completely and correctly. There is a star in the constellation Cygnus. It is not the brightest star in its celestial neighborhood. It is not the nearest or the most visually striking. On a clear, dark night far from the light pollution of cities and suburbs, it is barely visible to the unaided eye, a faint point of fifth magnitude among thousands of similar points, easily overlooked, easily passed by in favor of the more prominent stars that draw the casual observer's attention. Most people who have ever lived have never noticed it. Most people alive today have never heard its name. And yet this star has fundamentally changed our understanding of the universe. P Cygni taught us that stars are not permanent. They are not the eternal, unchanging fixtures of a crystalline firmament that the ancients imagined. They are dynamic, evolving, profoundly active objects, constantly interacting with their environment, constantly processing matter and energy through nuclear reactions in their cores, and constantly giving themselves away, shedding their substance into the surrounding cosmos, through winds and eruptions that operate on timescales from hours to millennia. The light that P Cygni sends us carries encoded information about its own dissolution, the spectral signature of a star caught in the act of losing itself, one radiation-driven atom at a time. That signature, the P Cygni Profile, has become one of the most recognized and most widely used diagnostic tools in all of astrophysics. It appears in introductory textbooks and in the most advanced research papers. It is stored in the databases of astronomical surveys spanning decades of observation. It is used to study the winds of hot, massive stars in our own galaxy and in galaxies billions of light years away. It is used to analyze the expanding ejecta of supernovae in the days and weeks following the explosion, when the outer layers are still accelerating outward and their spectral lines carry the unmistakable signature of matter in motion. It is used to characterize the outflows from active galactic nuclei powered by supermassive black holes millions or billions of times the mass of the Sun. It is used to study the accretion-driven winds of young protostars still assembling themselves from collapsing molecular clouds, objects at the very beginning of their stellar lives, showing the same spectral fingerprint as objects approaching the very end. The name P Cygni has become synonymous with the spectroscopic detection of outflowing material, wherever it occurs, at whatever scale, in whatever astrophysical context. This is the legacy of a star that once appeared without warning in a 17th century sky. A star that brightened to naked eye visibility in 1600, faded, returned, faded again, flickered unpredictably across the decades, and eventually settled into the quiet, steady luminosity it displays today. A star whose behavior baffled the astronomers of its era, who had no theoretical framework within which to understand what they were seeing. A star that, through its very refusal to behave like a proper, well-mannered celestial object, forced us to reconsider our most basic assumptions about what stars are and what they do. Stars lose mass. This three-word sentence is not an incidental footnote in the story of stellar physics. It is one of the central organizing facts of the entire discipline. The mass that a star sheds during its lifetime determines its evolutionary trajectory through the Hertzsprung-Russell diagram. It determines its chemical contribution to the interstellar medium and thus to the galaxy's evolving inventory of heavy elements. It determines the star's final fate, whether it ends as a white dwarf, a neutron star, or a black hole. It determines the type of supernova it produces, if it produces one at all, and the energy and chemical composition of the explosion, and it determines the mass and spin of the compact remnant it leaves behind, properties that are now being measured with exquisite precision by gravitational wave observatories, listening to the mergers of black holes and neutron stars across the cosmos. The difference between these outcomes can hinge on just a few solar masses of material lost or retained over the star's lifetime. A few solar masses, in a universe containing trillions upon trillions of stars, distributed across billions of galaxies, spanning an observable horizon 14 billion years deep. The loss or retention of a few solar masses from one individual star may seem like a small thing, but it is not small. Each massive star that lives and dies is a node in the vast network of chemical enrichment that connects the primordial cosmos to the present day. Each wind, each eruption, each supernova distributes elements that will become raw material for the next stellar generation. Remove stellar mass loss from the equation, remove the P Cygni profiles and the Wolf-Rayet winds and the LBV eruptions, and the universe remains a simple, sterile, unchanging place. Hydrogen, helium, radiation, darkness. P Cygni is part of this network. It is a living, active node, still contributing, still processing, still delivering. Its wind is blowing right now, at this very moment, as you listen to these words, carrying atoms of helium and nitrogen and carbon and oxygen outward from its luminous surface into the interstellar medium at roughly 200 kilometers per second. Those atoms are traveling outward through the concentric shells of previously ejected material that surround the star like layers of an onion, each shell the record of a past episode of enhanced mass loss. In a few 100,000 years, give or take the uncertainties that remain in our understanding of the star's evolutionary state, P Cygni will exhaust its nuclear fuel. Its iron core will grow beyond the Chandrasekhar limit and collapse in a fraction of a second. The shock wave generated by that collapse will tear through the stellar envelope and through the expanding shells of previously ejected material, lighting them up like a cosmic lantern, a supernova visible across the galaxy and perhaps beyond. The debris from that explosion will expand outward at thousands of kilometers per second. It will cool. It will decelerate as it sweeps up the surrounding interstellar gas. It will mix with the material already deposited by the wind, creating a supernova remnant of complex morphology and rich chemical composition. And in time, over millions of years, that material will participate in the formation of new molecular clouds, new protostars, new planetary systems condensing from the enriched ashes of a star that could not hold itself together. The process is ancient. It has been running since the first massive stars formed, less than 1 billion years after the Big Bang, in a universe that was composed almost entirely of hydrogen and helium, with only the faintest traces of lithium. Those first stars, sometimes called population 3 stars, were almost certainly enormous by present-day standards, with masses of hundreds of solar masses, burning with extraordinary luminosity and dying after lifetimes measured in mere millions of years. They had no rocky planets orbiting them. There were no heavy elements from which to build such planets. But their deaths, whether through supernovae or through direct collapse into black holes, seeded the cosmos with the first traces of carbon, oxygen, silicon, and iron, starting the enrichment cycle that has continued without interruption through the entire subsequent history of the universe, from the formation of the first galaxies to the assembly of our own solar system to this very moment. We are in the middle of that cycle, not at the beginning and not at the end. The Sun is a middle-aged star in a middle-aged galaxy, in a universe that is still, by most reasonable accounting, in the early chapters of its stellar era. The star-forming epoch of the cosmos has not yet reached its conclusion. There is more enrichment to come, more massive stars to form and burn and shed and die, more heavy elements to scatter into interstellar and intergalactic space. more worlds to condense from the accumulated chemical legacy of stellar generations stretching back to the dawn of cosmic time. P Cygni will contribute its share to that legacy. Indeed, it already has, through 4 centuries of documented mass loss and undoubtedly through millions of years of mass loss before any human eye observed it. And when it is gone, when the supernova has faded, and the remnant has dissolved into the general interstellar medium, its name will endure, not as the name of a star that anyone can see in the night sky, but as the name attached to the spectral profile it gave to science, the P Cygni Profile, a permanent fixture in the vocabulary of astrophysics, a diagnostic tool that will be used for as long as there are astronomers to use it, a reminder that the universe is not static, that stars are not eternal, and that the material from which we and everything we know is constructed was once part of something vast and luminous and beautifully, productively impermanent. The star is tearing itself apart, and in doing so it is building the future, atom by atom, photon by photon, wind by wind, eruption by eruption. The same forces that are destroying P Cygni are creating the conditions for everything that will come after it. This is the paradox at the heart of stellar mass loss, and it is not really a paradox at all. Destruction and creation are not opposites. They are the same process, viewed from different temporal distances and different spatial scales. From close up, measured on timescales of human lifetimes and distances of a single stellar system, P Cygni is a star in crisis. It is shedding its substance into the void. It is approaching the end of its nuclear burning life. It is, by any measure, dying. From far away, measured across the span of galactic time and the breadth of stellar populations, it is a source of renewal, a fountain of chemically enriched material, feeding the next generation of stars and worlds and possibilities. Both perspectives are true, both are necessary for a complete understanding, and in the tension between them, between the star's dissolution and the galaxy's enrichment, between the local loss and the cosmic gain, lies the deepest truth about the universe we inhabit. We are temporary patterns in matter and energy, briefly complex enough to understand our own impermanence and to marvel at the processes that made us possible. The atoms in our bodies are on loan from a cosmos that has been recycling them for nearly 14 billion years. One day, in the far future, they will be returned redistributed, reformed into configurations we cannot imagine, and incorporated into structures we cannot predict. The cycle does not end. It merely transforms, and each transformation carries forward the accumulated complexity of everything that came before. Somewhere in the constellation Cygnus, a star continues to glow, faintly, steadily, imperfectly, shedding itself into the darkness, writing its name in the ancient language of light and spectral lines and material loss, contributing to a story that began before the Earth existed and will continue long after the sun has exhausted its fuel and faded into a cooling white dwarf. P Cygni is a quiet star now, barely visible to the naked eye, easy to miss. But its voice, encoded in the blue-shifted absorption and red-shifted emission of its spectral signature, carries across the cosmos, telling the same truth it has been telling us for 400 years. Stars do not merely shine, they give themselves away, and in that giving, the universe renews itself.